remote controller, it will require a USB.
No, let's.
You have USB as well.
Yeah, I have a USB. Yeah, port. Yes.
So,
Okay. Then later I will just switch. Yeah.
okay.
Thank you.
Okay, fine.
Je vais aller en commander.
Okay.
So Muriel would like to interview.
Okay, fine.
Keep everything.
Try now. I would like to.
Want to take this with you?
Well, you just pour it out.
Tu peux faire attention, il tient un mordicus à son voilà, c'est juste. Pendant ce temps-là, je vais chercher un remote pour Francesca. Je vais juste la laisser là et je vais demander un remote.
Parfait.
Il y en a un. Il est où, Philippe? Il y en a un là. Ça, c'est un remote control, ça?
Oui, vous pouvez l'utiliser.
Ben
Il
oui,
est entré.
mais Francesca,
Oui.
c'est elle qui avait besoin d'un remote. Et Philippe vient juste partir en chercher.
Eh ben, écoutez, on en a deux ici.
On va lui montrer.
Très bien. On en a un ici. On en a un ici. Donc, je vous l'insère.
Et après ça, ça
Après, c'est tout simple, droite-gauche. Et ici, la
Très bien.
Normalement, ça devrait fonctionner. Vous avez vérifié, droite-gauche. Attendez. Oui, c'est bon, ça marche. Ça marche.
Ben, regarde, t'es là. Et tu vas le dérouler là. Comme ça, il peut vous expliquer. C'est
grand-chose.
pas un gros changement.
Oui, oui, c'est ça. Mais bien sûr, on va le passer, mais il y a la conférence de Kip Thorne.
Oui.
Après, il y a des questions. Donc là, on a des questions de la salle. Pendant ce temps-là, vous branchez le film.
Oui. Pendant les questions.
Oui, pendant les questions. Non, vous le branchez, non, pardon. Vous l'installez. Parce que moi, ma transition après, elle est très courte. C'est-à-dire que je ne présente pas le prix ici.
D'accord.
Vous voyez, donc ce timing sera un peu plus court.
Bonjour.
Et quand je vous dis, ce qu'il faut, c'est le préparer pendant les questions. Bonjour Patrick. Très bien.
Le film est déjà prêt, donc il n'y a pas de problème.
Voilà, d'accord. Donc,
il est sur un ordinateur, il n'est pas envoyé, j'ai plus qu'à envoyer les fleurs.
eh bien, écoutez, c'est parfait.
Et le film, il dure combien de temps alors?
19 minutes.
Ah, 19
marqué,
minutes.
là.
Je me rappelais pas.
19,
Je me rappelais pas que c'était si long.
Allez, 19 minutes.
Non,
Ah bah,
9 minutes.
Moi, j'ai 19 minutes de film.
Aïe. Ah, mais c'est juste sur les. Parce que moi, j'avais.
honor to be here. I'm very impressed by this. Francesca, for security, would you like to put that underneath my computer inside, if it's all right? Okay. Okay, it's your call. Thanks.
C'est bon? Bonjour à tous, bienvenue. Je suis très impressionné de voir toute cette foule dans la salle. Merci d'être venus. Mesdames, Messieurs, chers collègues, c'est avec grand plaisir que, en tant que directeur de l'école de physique des Ouches, je vous accueille à cette conférence d'exception ce soir à l'UGA et à la cérémonie de remise d'une médaille de l'UGA, la première lauréate d'un prix, un nouveau prix créé cette année, grâce à nos tutelles que vous voyez ici, le CNRS, le CEA, l'Université de Grenoble, Grenoble INP et l'ENS de Lyon, avec le soutien de l'Académie des sciences, prix qui sera remis à Francesca Ferlaino après la conférence de Kip Thorne tout à l'heure. Alors je voudrais donc remercier l'Université Grenoble de nous accueillir dans ses locaux pour cette cérémonie. Je voudrais vous dire un tout petit mot en commençant. Il y aura deux parties. Donc la première conférence, la conférence d'exception par Kip Thorne sur les très hautes énergies dans l'univers, la gravitation en champ fort. Et dans la deuxième partie de la conférence, on va aller dans le domaine des températures extrêmement basses, ultra froides, le nano-Kelvin au-dessus du zéro absolu. Et vous verrez qu'on va voir les deux, au cours de cet après-midi, voir les deux extrêmes de la physique dans la gamme d'énergie, des très hautes énergies et des très basses énergies. Alors, vous ne connaissez pas tous Cécile Dewitt-Morette, et ce prix a été créé pour honorer sa mémoire, et l'histoire de Cécile Dewitt-Morette est une histoire absolument fascinante. C'est une physicienne mathématicienne française qui a fait sa carrière tout au début, sa thèse avec Joliot et Curie en 1947, juste pendant la guerre et après la guerre. Et ensuite, elle est partie à Princeton où elle a rencontré son mari, Bryce DeWitt, d'où son nom. Cécile Morette, c'est la partie française, et Cécile DeWitt, c'est le nom de son mari. Elle a fait toute la suite de sa carrière aux États-Unis, mais dans son contrat de mariage, il y avait qu'elle devait rentrer en France 2 ou 3 mois l'été. Pourquoi? Parce qu'elle avait vu que la Seconde Guerre mondiale avait fait des ravages dans la physique française, elle s'était un peu désintégrée. Tous les grands physiciens, mathématiciens, physiciens étaient partis à l'étranger et elle a voulu faire quelque chose pour son pays. Et c'est ainsi qu'elle a eu l'idée de créer une école de physique dans ce lieu merveilleux qu'est les Ouches, le site des Ouches, dans la vallée de Chamonix, pour, après la guerre, former les jeunes générations d'étudiants français et d'ailleurs européens et même internationaux à la physique moderne telle qu'elle se faisait, en particulier à Princeton où elle était après pour la suite de sa carrière. Et donc c'est à l'âge de 28 ans seulement qu'elle a décidé, grâce à son pouvoir de persuasion, elle a débarqué dans le bureau du ministre de l'enseignement supérieur à l'époque en disant « j'ai besoin d'argent, eh bien supportez s'il vous plaît cette école ». Et c'est comme ça que ça a démarré. Et grâce à son pouvoir de persuasion, elle a fait venir les grands noms de la physique d'après-guerre, enseigner pendant 8 semaines aux Ouches, dans des pâturages, autour des vaches, etc., dans des conditions très rustiques. Et ça a lancé la réputation d'école de physique très vite, très très loin. Alors Cécile était aussi une montagnarde, et ceci va faire le lien avec la présentation qui va suivre, parce que cette photo prise de Cécile Dewitt et son mari Bryce en juillet 1962 a été prise par Kip Thorne, l'orateur qui va suivre tout à l'heure, quand il avait simplement 22 ans. Alors cette photo est très intéressante parce qu'on voit Cécile et son mari, mais on voit aussi les méfaits du retrait glaciaire. Parce que vous voyez le glacier du Tour qui est juste devant, là, à droite de la photo, il est gigantesque en 1962, il a beaucoup diminué. La face nord d'Aiguille Verte, en haut à droite, le couloir Couturier, le couloir Cordier n'ont plus du tout la même allure. Là, je parle pour les spécialistes de montagne, parce qu'il y en a plein à Grenoble, mais c'est une autre histoire. Voilà, et pour parler de la recette de Cécile Dewitt, c'était donc de mélanger des étudiants de tous les pays avec leurs professeurs sur le même site, un endroit un petit peu à l'écart de la vie de village, pour travailler ensemble, éplucher les patates ensemble au début et faire de la physique dans un cadre absolument merveilleux. Et le résultat, l'impact, c'est une liste très impressionnante de chercheurs qui sont venus enseigner aux Ouches. Aujourd'hui, il y a plus de 50 prix Nobel et médailles Fields qui sont venus enseigner à l'école de physique des Ouches. Et donc, c'est vraiment quelque chose dont la France et l'Université de Grenoble peut être fière. Voilà, donc je vais passer maintenant la parole avant de terminer en vous montrant le nouveau bâtiment dans lequel il y a les amphis. Il y a environ 70 places, 80 places pour les étudiants. Et le bâtiment central a été rénové en 1996-97. Et tous les gens sont très contents de venir travailler dans ce site. Et l'école fonctionne toute l'année, aussi bien l'hiver, comme on voit ici au mois de mars, que l'été, avec plusieurs formats, mais je ne rentre pas là dans les détails. Donc voilà, maintenant je passe à la présentation de l'orateur de cette première conférence cet après-midi, Kip Thorne, qui est un professeur de physique émérite à l'Université de Caltech, aux États-Unis. Ben oui, j'ai un peu mélangé. Je devais vous passer la parole, Lise Dumasy. Non, mais on va respecter l'ordre. Lise Dumasy, présidente de la Commu. Je suis désolé, je referai ma présentation juste après. Pas de problème. À vous la parole pour nous accueillir ici.
Bien, chers et chers collègues, chères doctorantes, chers doctorants, chères étudiantes, chers étudiants, chers auditeurs et auditrices venus en personne ou bien qui nous regardez derrière vos écrans, bonjour à toutes et à tous. En effet, c'est mon tour d'ouvrir comme traditionnellement ces différentes, comme je le fais, ces différentes conférences d'exception. Et aujourd'hui, je le fais donc pour introduire la conférence de Kip Thorne. Alors, mes mots seront sans doute toujours trop faibles pour décrire et ouvrir le moment d'exception que nous nous apprêtons à vivre ensemble. Un moment d'exception au cours d'une semaine, vous le savez, tout à fait exceptionnel, puisqu'il y a 2 jours seulement, nous accueillions le prix Nobel Gérard Mourou, qui nous illuminait de ses travaux sur les lasers. Et aujourd'hui, nous allons nous laisser irrémédiablement absorber par une conférence sur les trous noirs et les ondes gravitationnelles. Ombre et lumière. Avec vous, cher Kip Thorne, nous sommes bien décidés à suspendre ou à distordre légèrement le temps que nous nous apprêtons à partager très largement dans notre communauté universitaire et au-delà, puisque vous qui avez un parcours scientifique d'exception et qui avez un curriculum de récompense à faire pâlir les plus grands, vous connaissez aussi, et la professeure de littérature que je suis, spécialiste qui plus est des fictions populaires, ne peut y être insensible, un très grand succès littéraire, et vous avez lié recherche et fiction en entrant dans la culture populaire comme un des collaborateurs du scénario du film oscarisé Interstellar. Ce n'est pas de ça que vous allez nous parler aujourd'hui, mais c'est quelque chose qu'il m'intéresse de noter. C'est donc un très grand honneur pour nous tous de vous recevoir aujourd'hui. J'ajoute que pour s'adonner un peu plus à l'exceptionnel, nous avons décidé, comme il a été annoncé, de poursuivre votre conférence avec la célébration du Grand Prix de l'Académie des sciences, le prix Dewitt-Morette, nom de la fameuse fondatrice qui vient d'être évoquée de la Grande École de physique des Ouches. Cet événement aujourd'hui a donc un visage particulier. Je dirais qu'il a même au fond 3 facettes. C'est à la fois une conclusion, une continuité et probablement le début d'une nouvelle étape. Alors c'est une conclusion parce que l'événement vient couronner 10 jours de fête de la science. C'est 10 jours où nous avons accueilli de très nombreux publics, près de 20 000 selon les premiers retours qui me sont parvenus, et ce sur l'ensemble de nos campus à Grenoble et en Drôme-Ardèche. Parmi eux, tant de curieux, tant de néophytes, d'intéressés par les sciences ou de véritables initiés. Ce fut le plus beau des publics, en somme, fait de ceux qui viennent à la rencontre des sciences et de ceux qui la font ou qui la diffusent. C'est l'objectif de cet événement national que nous prenons grand plaisir à décliner ici au niveau local. C'est ce même objectif qu'affiche notre cycle de conférences d'exception: éveiller les curiosités, susciter les échanges, favoriser les rencontres autour de la science et du savoir en général, des rencontres qu'il est difficile de faire en dehors de ce que nous organisons aujourd'hui avec les plus grands. Alors c'est aussi une continuité, ai-je dit, tout simplement parce que cette nouvelle journée est la poursuite d'une programmation toujours plus riche. Depuis 2012, cet amphiveil et d'autres amphis, comme l'auditorium de Grenoble INP, ont vécu de très belles rencontres. Il y a eu bien sûr d'autres prix Nobel de physique, Dan Setman, Serge Haroche, Hiroshi Amano, Gérard Mourou il y a 2 jours, et bien entendu aujourd'hui, cher Kip Thorne, vous-même, mais aussi en chimie, avec Jean-Marie Laine, Ada Yonat, Jean-Pierre Sauvage, des scientifiques internationaux comme Thibaut Damour, médaille Albert Einstein, John Agnew de la British Academy, ou bien Valérie Masson-Delmotte du GIEC. Des penseurs reconnus de notre époque, comme Pierre Rosanvallon, ou dernièrement Michel Brunet et Yves Coppens du Collège de France, et Gilles Dowek, Grand Prix de philosophie, mais aussi des artistes primés, je pense notamment à Julien Prévieux. Ce tableau de conférenciers est, je dirais, le reflet de la pluridisciplinarité de notre communauté universitaire, de l'ensemble des secteurs du savoir et de la création qu'elle entend couvrir, et elle honore l'ensemble de notre communauté. Il s'agit là d'une grande diversité de domaines, de parcours, de thématiques, et pour autant, ces personnalités ont eu et ont un point commun, le souhait de partager leur savoir et leur passion auprès de, bien entendu, de nos collègues, des étudiants, mais plus largement de tous ceux qui s'y intéressent, et en particulier des collèges et des lycées, puisque à chaque fois, vous le savez, il y a un travail qui est fait auprès des plus jeunes, des collèges et des lycées de l'Académie, ce qui est aussi extrêmement important, auquel nous tenons beaucoup. Diffuser donc, évidemment, mais aussi et surtout faire connaissance, c'est l'ADN de notre cycle de conférences, avec vous aujourd'hui, cher Kip Thorne, et précédemment avec tous ceux que je viens de citer. Et demain, puisque j'ai dit que c'était aussi un début. Eh bien, je pense en effet que nous sommes à une nouvelle étape. Vous le savez, une nouvelle université, même si elle n'est pas totalement en rupture avec ce qui existe actuellement sur le site, Dieu merci, une nouvelle université va voir le jour et je suis bien persuadée qu'elle continuera à mettre en œuvre ce qui fonctionne, mais il ne faut jamais s'en contenter, il ne faut jamais s'endormir sur le succès. Et donc, j'appelle à ce que ce cycle de conférences irrigue toujours plus notre communauté, nos partenaires et notre territoire. Et je sais que les équipes qui s'y sont attelées jusqu'à présent en ont la capacité. J'ai donc la conviction que la programmation 2020 saura être aussi cette nouvelle occasion. Ce sera l'année de mise en branle de la toute nouvelle Université Grenoble-Alpes qui apporte une nouvelle dynamique au projet de culture scientifique et technique, de diffusion scientifique, de valorisation, en même temps qu'elle permettra le regroupement des forces et des ressources, et ceci toujours sous le signe et avec le souci du collectif. Je remercie donc tous ceux qui ont permis ce beau bilan et cette belle trajectoire. Merci à tous les conférenciers. Merci plus particulièrement à vous, cher Kip Thorne, qui nous faites l'honneur de votre présence aujourd'hui et qui allez nous faire l'honneur de votre présentation. Je souhaite remercier par ailleurs du fond du cœur les équipes qui travaillent à la programmation et à la réalisation des conférences et qui vont poursuivre ce projet dans un nouvel élan. Une pensée particulière pour celle que nous ne citons que très rarement et qui est pourtant la cheville ouvrière de l'ombre de ces conférences, Hélène Deschamps. Merci pour tout le travail accompli. Je remercie aussi l'Université Grenoble-Alpes qui nous accueille régulièrement dans ce magnifique amphivelle, qui vous accueille tous, et particulièrement pour cette séance d'aujourd'hui, son service communication qui a participé à l'organisation. Merci enfin à vous toutes et à vous tous qui avez été si fidèles et qui le restez. Et je vais à présent souhaiter évidemment une très belle conférence d'exception, une très belle rencontre avec Kip Thorne et repasser la parole à notre collègue pour introduire cette rencontre. Merci.
Bon, je vais être très bref parce que vous voulez voir de la science maintenant. Quelques mots sur Kip Thorne, qui est professeur de physique émérite à Caltech aux États-Unis. Il soutient sa thèse en 1965 à Princeton, puis rejoint Caltech où il fera toute sa carrière. Et Kip est un très bon ami de Bryce et Cécile Dewitt pendant toute sa carrière. Il est venu plusieurs fois enseigner à l'école des Ouches. Donc la photo datait de 62. Il est revenu enseigner après à 3 reprises en 1966, 1972 et 1982. Kip est un physicien théoricien, spécialiste de la gravitation, la relativité, les ondes gravitationnelles et les trous noirs, qui va être le sujet de sa présentation. Il a écrit plusieurs livres de référence, avec Meissner, Wheeler et Thorne, c'est une des bibles de la gravitation. Et puis aussi, il a collaboré à la réalisation du film Interstellar, et il a même écrit un livre sur la science de Interstellar. Alors, sa liste de prix internationaux est bien trop longue pour être répétée ici. Mais je vais mentionner seulement deux prix spéciaux. Le spécial Breakthrough Prize for Fundamental Physics en 2016, juste après la découverte des ondes gravitationnelles, découverte expérimentale des ondes gravitationnelles, qu'il partage avec Rainer Weiss, Ron Driver, et aussi la collaboration LIGO-Virgo, et bien sûr le prix Nobel de physique en 2017, partagé avec Ray Weiss et Barry Barish. Ce soir, qui va nous parler de trous noirs, ondes gravitationnelles, et Cécile Dewitt-Morette, souvenirs, découvertes et visions. Kip, it's a great pleasure to welcome you here in Grenoble, and the floor is yours.
I have my own. Okay, can you hear me? Not yet, not yet. We need sound and we need slide. Oh, you have slide? Wonderful, thank you. When I was invited to give this lecture on the wonderful occasion of the first award of the Cécile Dewitt-Morette École de Physique des Ouches Physics Prize to Professor Francesca Ferlaino, I was really thrilled to have that invitation, both because I already knew a bit about Professor Ferlaino's work, and it is very impressive, and because I was an extremely close friend of Cécile. And so I'm so happy to be here today on this very happy occasion. Let me say a few words about my dear friend Cécile. I first met Cécile and her husband Bryce at the École de Physique des Ouches, which she had founded in 1963 when I went there as a student to learn about relativity. We became close friends, and we hiked, going back to this picture, we hiked together on many occasions while I was there in '63 in the Alpes, and this is a picture of us on the Aiguille de Tours, the picture of Cécile and Bryce that, as you say, I took on the Aiguille de Tours. We also went hiking in 1968 in the Caucasian Mountains in Soviet Georgia and had a wonderful time together. In 1991, we went to the Salou Game Preserve on a 3-week foot safari organized by Bryce, which was just a fabulous event. Here we have, let's see, Bryce is here, Cécile, my wife, Carolee, Brandon Carter, and my son, Brett, and our guide, and I took the photograph. Cécile always took along a few books, typically books about mathematics or physics, and at siesta time, she would often be found in this position, reading and thinking. I suspect she was thinking about some of these same things while we were trekking as well, but she was a wonderful companion on these expeditions. Cécile was equally at home in mathematics and in physics. She was sort of the ideal mathematical physicist, whereas I, myself, am just an ordinary physicist, and so I relied on her on a number of occasions to give me advice. Let me just say about Cécile that she was among the very few kindest, most gentle, most generous, most persuasive, and most brilliant people that I ever knew. And for example, let me go back. I'll talk about the advice she gave me a little bit later. But from 1948 to 1950, she was a postdoctoral student at the Princeton Institute for Advanced Study. In the mornings, the first two people in were Cécile and Einstein. And so she and Einstein became friends as the early birds at the Institute. Freeman Dyson said of Cécile at that time, or looking back on that, when she was in the period between her age 24 and 26, Freeman, who is one of the most influential physicists of the entire epoch of my own career, he said Cécile was the brightest of the young physicists who arrived at the Institute for Advanced Study at the same time as I did. He arrived also at about that same phase of his career as she was. She was the first of the younger generation to grasp the full scope and the power of the Feynman path integral approach to quantum physics. There was an approach to quantum physics developed by Schrödinger, Heisenberg, and others in the 1920s, and that became the canonical approach. And Richard Feynman had just invented an entirely radically different approach to quantum physics, which turned out to be extremely powerful in his hands, in Cécile's hands, and in other hands. She, as Freeman said, she was the first of the younger generation to grasp the full scope and the power of the path integral approach. While I, Freeman says, was concerned with applying Feynman's methods to detailed calculations, she was thinking of larger issues, extending the path integral idea to everything in the universe, including gravitation and curved space-time. And so it was quite natural that when, for the first time in my career, I needed to understand this strange new approach to quantum physics, I turned to Cécile. And interestingly, that was when I was trying to understand backward time travel. I won't talk about time travel in this lecture. You can ask me if you want to in a question period. But I was trying to understand it and how it would work in quantum theory. And I quickly realized that the usual approach to quantum physics could not deal with the possibility of backward time travel, but Feynman's approach could. And so I turned to her to teach me about this and to give me insight into how to do this. She was a superb teacher, a superb classroom teacher, mentor, wrote superb books and lecture notes. And so in 1983, when I was trying to learn the theory of noise in these gravitational wave detectors that I'll talk about, it was she I turned to learn the mathematical underpinnings of that theory of noise, the so-called stochastic differential equations. And of course, she had written a set of lecture notes and problems on this topic, and so she gave that to me and said, here, this is where you should learn it, and I did, and it was really wonderful. Cécile, of course, as has already been remarked, played a major role in revitalizing physics in France and in Europe after World War II. She had the vision to create what at the time was called the École d'été de physique théorique, but it became the École de physique des Ouches, renamed some years later, when it became a year-round school instead of just being a summer school. This was a photograph I took when I was there the first time in 1962. This was the picture of the lecture hall as I remember it in 1962. And it had, this school had profound influence on physics worldwide. And I'm going to illustrate its influence as I talk about gravitational waves from my own career. Cécile, of course, as you may know, was made a knight in the French Legion of Honor, the highest, most prestigious society of for scholars in France, and for her contributions both to physics and to society in 1981, and she was promoted from knight to officer in 2011 as a token of the esteem of the French for Cécile. I want now to turn to black holes and gravitational waves. I'm going to tell you about this from my own personal point of view, and I'm going to focus in the early years in part on the impact that this Les Ouches school had on me and on this field. But let me begin by telling you what it was we discovered, what was the huge breakthrough in 2015. So 1.3 billion years ago, is it possible to turn down the lights here to see this movie better? 1.3 billion years ago, in a galaxy far, far away, there were two black holes that were circling around and around each other. Here you just see the shadows of the black holes in front of a field of stars. As they moved around, they create this pattern in the stars just through the bending of the light rays that come from the stars. We call this gravitational lensing. As they traveled around, they lost energy to gravitational waves. I'll tell you what a gravitational wave is in a minute. And so they spiraled together, coming closer and closer together, and then in a final cataclysmic collision, they emitted an extremely strong burst of gravitational waves. I'll tell you how strong in a few minutes. This burst of gravitational waves traveled out of the galaxy in which these black holes lived. They traveled into the great reaches of intergalactic space. For 1.3 billion years, they traveled across intergalactic space. 50,000 years ago, think of it, when our ancestors were sharing the Earth with the Neanderthals, was when this burst of gravitational waves arrived at the edges of our Milky Way galaxy. For 50,000 years, these waves traveled through the Milky Way galaxy, arriving at Earth on the 14th of September 2015. They arrived first at the Antarctic Peninsula. They traveled up through the Earth unaffected by all of the matter in the Earth. They emerged first at our LIGO, Laser Interferometer Gravitational Wave Detector Observatory in Livingston, Louisiana. I'll tell you about this observatory in a few minutes. And 7 milliseconds later, they arrived, came up through the Earth at the detector, the LIGO detector in Hanford, Washington. They stretched and squeezed this instrument in a way that I will talk about in a few minutes. That put a signal then into a computer which was scrutinized by the team that had built these instruments and was analyzing these instruments. A 1,000-person team of LIGO scientists and Virgo scientists here primarily in France and in Italy. And this collaboration worked for 5 months to be absolutely sure that what we had seen was gravitational waves, and then announced the result on February 11 of 2016, and it was front page headlines in all the major newspapers around the world. Let me tell you how we got here and some of the implications of this from a personal point of view, and tell you the impact that the Les Houches School had on this. This really began back in 1916 with Albert Einstein, who predicted gravitational waves. He said that if a gravitational wave propagates into this screen, it will stretch space horizontally and squeeze space vertically, transverse to the direction of propagation. And the next moment, it will stretch space vertically and squeeze space horizontally. Another way to say this is 2 inertial frames, one here and one there, will move back and forth relative to each other. That's what I mean by stretching space, which means that if I have a particle at rest here inertially and one at rest there inertially, they will move back and forth relative to each other. So this is a pattern of particles, each of them behaving inertially, just floating out in interstellar space, affected by a gravitational wave. Being stretched and squeezed, the pattern is stretched and squeezed. Einstein, in his seminal paper on this, made estimates of how strong these gravitational waves were, and he said, in effect, that these waves are so weak that they will probably never be seen by humans. But they were seen approximately 100 years later. It took that long. So coming back to myself, Cécile's Les Houches summer school in 1963 was on relativity and related mathematics, and I went there as a student. That was where I learned relativity theory and got exposed to gravitational waves. This is a picture that I took of friends and colleagues at the Les Houches Summer School. Here I am at the lecture hall. John Wheeler, who became my PhD thesis advisor, he lectured there about black holes, neutron stars, and the dynamical behavior of warped space-time, which he called geometric dynamics. Ray Sachs lectured about gravitational wave theory. Joe Weber lectured about gravitational wave experiment. And so it shouldn't surprise you that having been exposed to these wonderful ideas before gravitational waves were seen, before black holes or neutron stars were ever seen, but having been exposed to this in Les Houches, I decided when I became a young professor that this is the direction my research would take me. By the way, then, the lectures, the marvelous lectures at that Les Houches summer school were, of course, published in a book that was edited by Cécile, as she did with year after year these summer schools. So in 1966, when I went to Caltech, I created a theory group, a group of theorists like myself, working on black holes, neutron stars, and gravitational waves, motivated, I said, largely by what I learned at that 8-week-long summer school in Les Houches. I was back in 1972 at Les Houches as a lecturer, lecturing on black holes. And this was the golden age of theoretical research about black holes. And I was just beginning to suspect that black holes, when they collided, might produce gravitational waves. This is a photograph of myself, Bryce DeWitt, Cecile's husband. Here I am. I've just given a lecture about propagation of radiation through hot disks of gas around black holes at the summer school. Stephen Hawking was there, and he had a huge impact on all of us there. It was a marvelous summer school in which Stephen and colleagues formulated the laws of black hole mechanics, the definitive theory of black holes before quantum physics is brought in, was developed there. I developed, together with Igor Novikov while there, the relativistic theory of these hot disks of gas around black holes, and was just beginning to think about gravitational waves from black holes. Again, this is my well-worn copy of the volume that came out of that summer school, very, very, very well-worn. In that same year, 1972, my students and I began to develop a vision for what we could do with gravitational waves if they could be detected. And the key point, as we realized, was that the principal way we had to observe the universe at the time was electromagnetic waves, light, X-rays, radio waves. Electromagnetic waves are oscillations of the electromagnetic field that travel through space as time passes, whereas gravitational waves are oscillations of the very fabric or shape of space itself, stretching and squeezing. Electromagnetic waves are what we call technically an incoherent superposition of emission from particles, atoms, and molecules that have electric charges, whereas gravitational waves are emitted in a radically different way. They are coherent emission by bulk motions of large amounts of matter or energy. Electromagnetic waves are all too easily absorbed and scattered when they travel from their source to Earth, whereas gravitational waves are never significantly absorbed or scattered, even if they're created near the Planck era when the universe was born. They still travel, bringing information then potentially about the birth of the universe, and I'll comment on that at the end of my little talk. Implications of this: many gravitational wave sources won't be seen electromagnetically, and indeed there was no electromagnetic emission, no light, no radio waves, no gamma rays, no X-rays from the colliding black holes that we first observed. And huge surprises are likely because this is such a radically different kind of radiation from electromagnetic waves. You'll be seeing radically different things than one has seen with electromagnetic waves. So that was my motivation, and it seemed to me clear, if this could be done technically, then I should devote much of my career to helping make it happen. That same year, within a few months of when we wrote our paper describing our vision, Ray Weiss at MIT proposed a design for a gravitational wave detector, the first version of a design of what we would ultimately build. He had 4 mirrors that hung from overhead support, so we're looking down right now on these mirrors. And when the gravitational wave came along, it would push these mirrors together while pushing those apart, then push these together when those are pushed apart. And so he said, let's send a laser beam in, split it in half, so half of it goes in here, throw a hole in this mirror, and bounces back and forth many times. These mirrors are closer together than they were before the wave arrived, and so this beam will travel back and arrive back slightly sooner than the half of the beam that goes in here and bounces back and forth. And so the interference of those beams will, through a phenomenon called interferometry, will produce a change in the intensity of the light that comes out in this direction, going toward a photodetector that detects the light. So that was his basic idea. I looked at this and I thought that he was crazy. There was no way this was going to work. But I was a gentle person, not as gentle as Cécile. I was a kind person, not as kind as Cécile. So I wrote in a classic textbook on which I was a co-author that this idea was not very promising. Let me explain why I wrote that. I knew already at that time that the approximate strength of these gravitational waves would be such that the change in separation of the mirrors divided by the separation that they had would be about 10 to the minus 21. That's a very small number. That, in fact, turns out to be the strength of the waves that we actually discovered in 2015. But already we were talking about this strength of waves. That meant that if we had mirrors separated by 4 kilometers, these mirrors would move by 10 to the minus 17 meters. Now let me, even for the physicists, remind you how small that is. We take 1 centimeter, divide it by 100, you get the thickness of a human hair. Divide by 100 again, you get the wavelength of the light that Ray Weiss said he would use in this measurement. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 100 again, and you get the motions of these mirrors. There's no way you could possibly do that. That was about 1 trillion times smaller than the wavelength of the light that Ray Weiss said we should use. And so I just didn't believe it was possible until I spent 2 years, part-time of course, studying Ray's technical paper on this, in which he actually identified all of the most important sources of noise that you would have to overcome to have success here, and described how one might deal with them and estimated what kind of sensitivity you could achieve with these instruments. Oh dear. Dropbox wants something. And excuse me a moment while I deal with this darn thing. I don't know why now where's my cursor? It's never happened in the middle of a lecture before. No? Okay, I want to cancel. Come on, let's cancel. Okay, now we'll go back. Okay. So anyway, I studied his technical paper and saw that conceivably it was possible, and I had detailed discussions, one all-night long discussion in Washington, D.C. when we were there for a meeting of a committee that he chaired with Ray, and then a colleague, Vladimir Brzezinski, in Moscow, who was one of the really great experimental physicists of that era. And between them and studying this, I finally became convinced that this might succeed. And so I set out to do everything that I and my research group of theorists could to help them make it a reality. So once I was convinced, we made a decision to create a gravitational wave experiment group at Caltech. We brought a man named Ronald Drever from Glasgow, Scotland, to lead the effort. And the reason we brought him, one of the primary reasons, is he had invented a very nice improvement on Ray Weiss's scheme, in which these mirrors, in which the laser beam here did not go back and forth making many spots on the mirrors. All of the spots overlapped. And the light was caught temporarily and between these mirrors and still bounced back and forth many times. In what is called a Fabry-Perot cavity. I don't want to go into the details, but this was a much simpler scheme, but harder to make work. But he had the courage to think he could make it work, and we did make it work. The team made it work in the end very successfully. It was a significant improvement, and so we brought him to lead the effort at Caltech. From 80 to 83 then, at Caltech, under his leadership and the leadership of Stan Whitcomb, they built a 40-meter prototype, an interferometer 1% as long as what we would ultimately build, but that's pretty long. While at MIT, Ray and his team were completing a 1.5-meter prototype and doing a feasibility study for kilometer-long interferometers. So this is how we got started, And then, right at the critical point where we were about ready to propose doing this to a funding agency, Cécile's summer school of 1982 was on gravitational waves. And we all went to Les Houches for the summer school. And we had lectures on the theory of gravitational waves. I gave lectures on sources of gravitational waves, black hole binaries, neutron stars colliding, and so forth. By that time, I and others had done a lot of work on what would produce the waves. There was lectures and a lot of discussion of how you calculate the shapes of the waves, which would be crucial for the future. And a lot of work and discussions about computer simulations of colliding black holes, other sources of waves, and ideas and work on experimental design. And it was there, in fact, that Drever had one of his most brilliant ideas for something called signal recycling that I won't go into, but and which was improved on by a young guy in his research group back in Glasgow named Brian Mears a few years later. So at these summer schools, it wasn't merely lectures to students. It was the professors and the students brainstorming together and getting key new ideas. Stephen Hawking's and Hawking, Bardeen, and Carter, their theory of black hole mechanics, the improvements on the experimental design for our gravity wave detectors, and key new insights into numerical simulations and sources, all coming out of the summer school discussions. And of course, again, a volume that came out of the summer school discussions. In 1984, shortly after this summer school, MIT and Caltech, that is Ray Weiss and our group at Caltech, the Drever and me, we proposed building LIGO, the Laser Interferometer Gravitational Wave Observatory. And now I'm going to skip forward, just tell you, there's 33 years from then until the success. There's 33 years of intense work by a team that grew to more than 1,000 scientists and engineers, led by somebody who really knew how to lead large projects and organize them, a guy named Barry Barish. Barry realized that these instruments were so complex that you had to have a large team, and he expanded the team to 14 nations, to 80 different institutions, to 1,000 scientists and engineers. In 2001 to 2010, when we proposed to build this, we said we would have to build 2 generations of instruments before we were likely to see anything. First generation we built as we had proposed. We proposed in 1989. Our first generation was built and operated 2001 to 2010. 2010 to 2015, the second generation, which we had claimed when we made our proposal would be the first ones to see the waves. They were installed in our facilities in Hanford, Washington, Livingston, Louisiana. September 14, 2015, here's an aerial view of the instrument, the interferometer, with long beam tubes in which the laser light's bouncing back and forth in the desert in Hanford, Washington. 3 days before our first search with the advanced instruments was supposed to begin, the first signal arrived. Fortunately, the instruments were almost ready. They're very complex. There were lots of things had to be tuned to get them precisely right. They weren't quite precisely right, but they were easily good enough to see that first signal. And it came in, and the director of LIGO said, our first search has begun today, a day early, at the moment the signal came in. And we continued our search and saw several more black holes colliding. That first signal, how did we know what we were seeing? After the signal was cleared up, I'm plotting stretching of the mirrors apart and pushing them together as a stretching up and squeezing down as a function of time. So it's stretch, squeeze, stretch, squeeze, stretch, squeeze along one of the arms. And the gray signal is the trace of what the signal was. And the red is from numerical relativity, solving Einstein's equations on computers, which was the key thing that we were pushing already at the Les Houches Summer School in the 1980s. By making the comparison, we could go back to the numerical relativity calculations and infer then, through the comparison, that the initial black holes weighed 29 and 36 times as much as the sun weighed, for a total of 65 solar masses. But the final black hole was only 62 solar masses. It's as though you had annihilated 3 suns and turned all of their mass into gravitational waves. That's how much energy came out. And it came out very quickly, in about 1/10 of a second. So the power output, that's the energy per unit time that came out, turns out to have been 50 times larger than the total power from all the stars in our universe put together. 50 universe luminosities, 50 universe powers in 1/10 of a second, which carried then a total energy of what you get by annihilating 3 suns. It was the most powerful explosion that humans had ever seen any evidence of, except the Big Bang birth of our universe. By far the most powerful explosion. No light, no X-rays, no gamma rays, no radio waves. Only gravitational waves. We would never have known about it if we didn't have this new form of wave to bring us information about the distant universe. We could then go back to the simulations and see what was happening. And what I have to explain this is that black holes are made from warped space and time. Gravitational waves are made from warped space, stretching and squeezing of space. Black holes similarly made from warped space and warped time, not from matter like you and I. So to visualize the warped space of a black hole, we take a 2-dimensional surface that goes through, this is for 2 black holes, it goes through the orbital plane of the 2 black holes. And that's a curved surface. It's not flat like a flat sheet of paper. So to see the curvature, we then imagine embedding it, putting it in a higher dimensional flat space to see the curvature, the warping. And it turns out, as many of you will know, that the warping then looks like a funnel for each black hole. So there's 2 funnels here that are the black holes. And the color coding is the slowing of time around the black holes, a second aspect of the warping. And I'm going to show you then this movie that comes by having compared the wave shapes with what was observed, and going back and looking at the simulation and make a movie of how the warped space and time behaved. So we're going to slow the movie down as the black holes now are nearly ready to collide. This is 0.016, 0.012 seconds before the collision. It's like a huge storm in the ocean, and the ocean flashing up in a huge storm, then coming back down and oscillating and dying out, and a power output in those waves of 50 universe luminosities. So that was what was actually happening. That's like mapping, like observing the physical behavior, say, of 2 objects that collide. Here, the objects are made from warped space-time. By August 2017, we had seen several black hole mergers, but we did not have very good resolution of where they were on the sky. The very first one, which was 150914, that means it came in on September 14, 2015. This is a sphere that represents the sky around the Earth, and the source was somewhere in there. We knew moderately well where it was north-south, and that it was coming in more or less overhead at the tip of the Antarctic Peninsula. We knew that because the signal arrived first at Livingston, Louisiana, and then later at Hanford, Washington, with a time delay of 7 milliseconds. Livingston is south of Hanford, so the source was in the south. Okay. And, but fortunately, in August of 2017, a second gravity wave detector came online, the Virgo gravity wave detector here in Europe, this what is then a French, Italian, Netherlands, Poland, Hungary collaboration. And then with the help of Virgo, we could pin down where that really was on the sky quite well. And after this August 14 event, 3 days later, the 3 detectors working together saw a collision of 2 neutron stars. Each neutron star was made from pure nuclear matter, diameter of about 30 kilometers, mass of about 1.5 times what the sun weighs, orbited around and around each other, spiraling together as they emit gravitational waves. They came crashing together and created a gigantic fireball of hot nuclear matter flying out into space. And that is real matter, so it emits electromagnetic waves. It was called a kilonova, is this type of event. Nobody had ever seen a kilonova before, but people had worked on the theory of them. And so this was the gravitational wave signal at the 3 sites, depicted in a form I'm not going to explain. 1.7 seconds after the gravity waves for the collision arrived, there was a burst of gamma rays, very high energy or high frequency electromagnetic waves came in. Our location on the sky for the gravity waves was this little error box here. The gamma rays were coming from an overlapping region that was much larger because their angular resolution was not as good as ours. And then, over the next few hours, X-rays, ultraviolet, optical, infrared, radio waves, all forms of electromagnetic waves. It was the most intensely studied event in the history of astronomy. Something like 20% of the world's astronomers observed this with different kinds of telescopes. It was the beginning of what we now call multi-messenger astronomy, each type of radiation being a messenger. And one of the things we learned from the electromagnetic observations was that, as had been predicted, a huge amount of gold and platinum were created in the collision of those 2 stars. So much that it's likely that most or all of the gold and platinum here on Earth came from neutron star collisions. So this is the beginning of major new insights into the universe that come from combined electromagnetic and gravitational waves. We've now done 2 major searches for gravitational waves, and our 3rd search started on April 1st, 2019, with improved interferometers. You can get for your smartphone an app. It's called GW Events. And every time a gravity wave signal arrives, seen by LIGO and Virgo, within 1 hour, automatically, by the computer systems that are doing the analysis, information goes out to you. Your your smartphone goes whoop. That's a chirp. That's what a gravitational wave signal would sound like if you put it on a loudspeaker. And then you go in and you look, and if this was the most recent one, which was on September 30th of 2019, these instruments were shut down for 1 month. The month of October, they're shut down for some improvements. Then you go in and you click on this and you see all the details of the signal that were obtained in that first hour. And so by now there's more than 30 such signals seen in those last 2 months before it was shut down temporarily. There were 10 events seen, so about 1 a week. 5 of them were collisions of black holes. 1 was a collision of 2 neutron stars. 2 of them were a black hole swallowing a neutron star whole. And 2 were a black hole swallowing something we're not sure what it is. Because it has a mass between 3 times the mass of the sun and 5 times the mass of the sun, and we're not sure whether these are neutron stars or black holes in there. Nobody had ever seen any compact objects in that mass range. So this is what is going on. Looking forward just a couple of years, we will then be at a point where these instruments are monitoring the motions of 40-kilogram mirrors to a precision that is so exquisitely small that these mirrors will jiggle back and forth due to quantum physics. We know that an electron inside of an atom, you can never say precisely where it is. You can only say a probability that it's here, there, or another place, because it's jiggling around due to quantum mechanics. Our mirrors jiggle around. For physicists, we measure the center of mass motion of the mirrors. And the centers of mass jiggle around at this level of 10 to the minus 19 meters. And we will be then at the point where we're measuring motions at the level of this quantum mechanical jiggling of the mirrors. For the first time then, humans will be seeing human-sized objects behave according to quantum physics, jiggle randomly, unpredictably, unstoppably. And so it's been necessary to develop something called quantum non-demolition technology to deal with this. This is a whole new form of technology that's closely related to quantum computing, quantum information science, quantum communication. I won't go into the details, but in fact, this is what my own research group, together with Vladimir Braginsky's research group, who was really the pioneer of this subject, focused on with a large portion of our effort from 1980 up through the present. And my former research group, I'm now retired, is continuing to push on this new technology. By the late 2030s, 20 years from now, the successors to LIGO and Virgo, which are called the Einstein Telescope here in Europe and Cosmic Explorer in the US, new instruments much larger and unfortunately more expensive, will likely see gravitational waves 20 times weaker than today, see every black hole collision in the universe with masses less than 100 times the mass of the sun, and a variety of other warp side phenomena and huge surprises, I expect. Also, by the 2030s, gravity wave detectors will be operating in 4 different frequency bands. It's as though in this period of about 20 years, we had turned on optical astronomy, radio astronomy, X-ray astronomy, gamma ray astronomy, all turned on in 20 years. In particular, LIGO, Virgo, and their ground-based partners and successors will be looking at gravitational waves with millisecond periods of oscillation of the stretching and squeezing. An instrument called LISA, which consists of 3 spacecraft that track each other with laser beams, and is being built and planned and built by the European Space Agency. We'll be looking at gravitational waves with periods of minutes to hours. The ratio of these periods to those periods is the same as radio waves to light. So it's as though LISA is radio astronomy and LIGO and Virgo are optical astronomy. And with LISA, we expect to be seeing collisions of black holes that are very heavy, 1,000 to 10 million times as heavy as the sun. And we expect to map the warped space-time of quiescent black holes with exquisite precision. And we expect, quite possibly, to look back and see gravitational waves that came when the laws of physics changed, when the universe was 1 trillionth of a second old, in what is called the electroweak phase transition. Before that, electric and magnetic fields didn't even exist. And the equations called Maxwell's equations that control them were irrelevant. There was this so-called phase transition. That phase transition in which they were born, electromagnetic fields were born, if it was what's called a first-order phase transition, then it should have produced strong gravitational waves that LISA will see. There's a technique, I won't go into the details, called pulsar timing arrays that will see gravitational waves with periods of years to decades and look at extremely heavy black holes up to the heaviest that exist in the universe. And finally, again, another technique I won't go into called CMB polarization, looking at gravitational waves with even longer periods, hundreds of millions of years. Of course, that's longer than a graduate student lifetime, so you can't have a graduate student there monitoring the waves. But instead, what you do is you look for patterns on the sky in microwaves. With this instrument, we expect to see the birth of the universe, gravitational waves from the Big Bang, birth of the universe, amplified by a phenomenon called inflation in the early universe. And the details of the waves will be then a combination, a so-called convolution of what happened in the birth of the universe and what happened as the universe expanded very rapidly early. And similarly, we will expect to see the same thing with very different wave periods of a fraction of a second, using a space-based successor to the LISA mission in the middle of this century. And so I look forward eagerly to the middle of this century. I was born in 1940. I plan to live to 110. So they need to get this by 2050, or I'll be very disappointed. But I look forward to having the observations come in about the gravitational waves from the birth of the universe and have them be different from what the theorists predict, and completely upset our thinking about the laws that govern the birth of the universe, the so-called laws of quantum gravity. So let me just conclude by saying it's 400 years since Galileo built a small optical telescope, pointed it at Jupiter, and discovered Jupiter's 4 largest moons, and thereby created modern electromagnetic astronomy. It's just 4 years since LIGO turned on, discovered the gravitational waves from colliding black holes, and created gravitational astronomy. Our understanding of the universe has changed enormously in the 400 years since Galileo. And I expect, and I invite you to speculate, that there will be similarly huge changes in our understanding of the universe in the next 400 years by the joint observations with electromagnetic waves and gravitational waves. Thank you.
Thank you very much, Kip, for this fascinating presentation. All the audience was subjugué, as we would say in French.
Well, I do apologize. I do apologize. He did not speak in French. I have barely enough understanding to order in a restaurant. So
this was very, very clear and fascinating. Yeah. We have time for a few questions. On a du temps pour poser quelques questions. Vous pouvez les poser en français ou en anglais américain. Et c'est l'occasion de poser quelques questions à Kip. N'hésitez pas. Micro.
Hello, I would like to say that it's an honor to have you here. I was just wondering, you said that Cécile gave you an advice, but you didn't have the time to mention it, so
well,
I would really like to hear.
She gave me much advice over the period of my career. I think maybe the most important thing that I learned from her is be kind and gentle with colleagues, but be very persuasive. And I think it's true that my biggest contribution to gravity waves has been being very persuasive in the Cécile manner. And I tried to emulate her. I wasn't as good at it as she was, but I think I was probably the best in our field at emulating her, and that's my contribution, biggest contribution to why we're here.
Thank you so much.
Well, perhaps you're a little too modest on that side, right?
No, it's my biggest contribution. There's no question. But I made other contributions, but selling this, convincing Caltech, then the National Science Foundation, and ultimately Congress that we should do this. This wasn't easy.
No, I followed myself a little bit. Also, the European side hasn't been easy also. Yes. Yes?
Hi, Kip. A question on backward time travel and quantum physics. In some interpretations in quantum theory, there's a thing that when you detect something, there can be this multiple world or parallel universe phenomenon. It's not always accepted by everybody. But when you do backward time travel, can you pick a particular parallel universe, or would you just end up in a random one? This is a bit of an amusing question.
So I have not thought about backward time travel in that context. So this is, the remark has, so for backward time travel, I was trying to do a real calculation with a very simple problem where a billiard ball goes into a black hole, into a wormhole, comes out of the other mouth before it went in, and hits itself, preventing itself from going in. And how do you resolve that question? Well, I figured out how, with students, how you resolve it. In classical physics, in quantum physics, it's much more interesting. So it's a very simple little thought problem. And I found that the way to deal with this really was with Feynman's approach, to which Cécile had contributed so much. with regard to many worlds, there is an interpretation of quantum physics that looks to be totally crazy, that whenever you make a measurement, something that was quite random and was described by a probability that a particle is here, different probabilities here, different probabilities there. When you make a measurement, suddenly it is at the location you measured. So what happened to all the other probabilities? And the idea is that they all went into other universes, and the universe split into many universes when you made a measurement. And so I always thought that this was a rather wild and crazy idea. But Bryce DeWitt was among the people who took it seriously. But my big surprise was when I had a discussion with Richard Feynman, who has had deep physical intuition, and over lunch in a local joint in Pasadena. And I asked him, when pushed to the wall, what's your interpretation of quantum mechanics? And he said, it's many worlds interpretation. He said, I don't like it, but I don't know anything else that will make me feel even semi-satisfied. So this seemingly crazy idea really is taken seriously by people like Bryce and Richard Feynman. I'm not so deep in the subject, but for practical calculations, I think people generally don't use it. You need a precise mathematical formalism, which is what Feynman had given to us in his so-called path integral approach. What Cécile actually made that formalism much more rigorous mathematically and showed us how powerful it was. And that's what I learned from Cécile in order to do my practical calculations about time travel. Yeah.
Thank you. Time for one more question. Two more, the last two questions, there and there. Yes.
Hello?
Wait the microphone.
I don't have a very strong voice, but we are too much. Okay, I'm so pleased to ask this question to you, and it's just about something. When you talk about neutron stars crashing together, both gravitational waves and radiation is formed, while, for instance, just when two black hole crashes, just gravitational waves are produced. Now my question is, why in the first case both waves are produced and in the last just gravitational waves?
So electromagnetic waves are produced always by oscillating electrical charges. And electrical charges is one aspect of real matter, neutron star matter, the matter of which you're made. Gravitational waves and black holes have no electrical charges. They're not made of matter. They're made from warped space and time, as I described. And so they can't produce electromagnetic waves, no electric charge to oscillate. Whereas the neutron stars, they have both very strong gravity, warped space-time, huge masses that can generate gravitational waves, and they have the electrical charge that will produce light, radio waves, X-rays, gamma rays, infrared, all forms of electromagnetic waves. So that's what we saw.
Yeah. Here.
One last question here.
Here, it's here. Hello? I was first here. Oh. Yes. Hello, here. Yes.
Okay.
Yes,
okay.
In the middle.
Your turn there. Yes.
Thank you.
We have lots of light here, we don't see you.
Okay. Thank you for this unbelievable experience. It's more than amazing, it's more than my words can say. It's unbelievable to think how amazing it was, like in the summer schools. A lot of physicians brainstorming about everything, amazing. So my question is, what is your personal opinion about the supermassive black holes in the middle of galaxies? why, sorry about the word, why the fuck they are there, where they came from, why do we have some supermassive black holes in the middle of the galaxies? Thank you.
Well, it is quite striking that most every massive galaxy that we see has a supermassive black hole in it. I don't know whether there are exceptions. I don't know of exceptions. And so it makes you tempted to guess that these supermassive black holes played some role in the birth of the galaxy itself. And there are speculations along that direction. And so that's one possibility. There are other possibilities, and various hypotheses have been made, but that's a common speculation. The LISA will tell us a lot about these supermassive black holes when it is operating through gravitational wave observations. And of course, electromagnetic observations are also telling us a lot, but okay. Let me just leave it at that.
Do we have time for one more question? Thank you. This is rather a personal question. So many researchers and scientists want to make huge impact in their fields, and it's hard. And somehow you did it. So I wonder, like, do you have some, like, secrets to share with us?
Well, the first thing I would say is that we did it because we had a superb experimental team of 1,000 people, scientists and engineers, and that was what was required for success. We would never have had success without them. And so one key is knowing what you need for success. Some pieces of science can only be done by highly cooperative, highly coordinated, large teams. Other things are best done by one or two or three people working very closely together. You need to know which it is. Another thing in terms of personal advice is that we all have different personalities. I don't like working in large teams, but we had to have a large team for success. But I chose from the outset to work in a field where almost nobody else was working because I really enjoyed it, and I knew that if I had fun at it, that it would be a lot easier to do it successfully. And so my grandfather said to me when I was 4 years old, I remember it vividly, he said, when you grow up, you find a job that's like play, you will have succeeded. But I knew, well, after a while, when Barry Barish educated me properly, I knew we had to go big for this, and it would no longer be as much fun for me. But the first 30 years were enormous fun. And then it ceased to be quite as much fun, but we did it that way because that's the way it needed to be done. So I don't know what I can offer, but besides those remarks.
Yeah. Well, your message is follow your enthusiasm and your intuition.
Yes.
And get trained by attending.
And if you need to work in a large team, make sure the team is really very, very good.
And motivated.
And motivated.
Yeah. Thank you very much. So I think it's time to thank Kip again. Now we have a 10 minutes movie about the Les Ouches School, which was taken some years ago, which will be very interesting. And then we switch to the second part, which is devoted to the medal and the movie where we go to very low temperatures.
It's really wonderful.
Oh, thank you.
Du haut de ces sommets, 50 ans d'histoire de la physique vous contemplent. C'est ici, non loin de Chamonix, dans les Alpes, que la physique moderne française est née. Habituellement très spécialisée et studieuse, l'école des Ouches, ce 28 juin 2001, fête simplement son demi-siècle d'existence.
Là, on vous aura numérisé sur tous les angles, hein, là, il n'y a pas de problème.
Ce lieu exceptionnel de débat a su accueillir et former un nombre impressionnant de prix Nobel.
Vous pouvez vous disloquer. Après la condensation.
Anciens élèves et professeurs ont profité de l'occasion pour rendre hommage à sa fondatrice, Cécile Dewitt-Morette. Dès après-guerre, cette physicienne a eu la chance de faire des études auprès des plus grands de la physique mondiale, en Irlande, au Danemark ou aux États-Unis. C'est grâce à ces rencontres qu'elle a pu convaincre autant de personnalités de la suivre dans son projet un peu fou.
Je comptais rentrer à Nancy, prendre un poste de maître de conférence à la rentrée de 1950. Mais au printemps 1950, Bryce DeWitt, un jeune Américain, me demande en mariage. Ma première réaction, c'est de refuser parce que je voulais rentrer en France pour aider la physique à redémarrer. Mais je regrettais de refuser parce que je l'aimais bien. Tout d'un coup, et en quelques minutes, j'ai pensé qu'il y avait une...
De l'idée à la réalisation, les choses vont très vite. En moins d'une année, la jeune physicienne établit son programme de cours et surtout, elle se décide pour un lieu situé à 4 km du petit village alpin des Ouches. Ici, les étudiants trouveront la concentration maximum nécessaire à un travail d'une intensité inhabituelle. Et les professeurs, étrangers pour la plupart, pourront allier l'utile à l'agréable en faisant venir leur famille.
La France, bien sûr, venait de subir une terrible expérience au cours de la Deuxième Guerre mondiale. Et en 1951, elle ne s'était pas encore vraiment remise de cela. Alors que dans d'autres pays, par exemple en Grande-Bretagne ou aux États-Unis, d'abord, il y avait eu d'importants travaux durant la guerre. La France était occupée et rien n'y était vraiment possible. Et deuxièmement, ces pays s'étaient très rapidement redressés, particulièrement les États-Unis après la guerre. Et donc des choses très excitantes avaient lieu en dehors de France, pas encore en France.
Il faut quand même réaliser qu'en 1951, en 1953, l'enseignement de la physique moderne en France était inexistant, nulle part. Nulle part. Il n'y avait pas de cours de mécanique quantique à la Sorbonne, il y avait le cours de De Broglie, mais personne n'y comprenait rien. En ces cas, on n'y allait pas. Et les cours de physique des universités s'arrêtaient en 1880. La physique moderne était complètement inexistante. Ce qui fait que notre génération a appris la physique moderne ici.
Après le choix des lieux et des professeurs pour dispenser cet enseignement, il fallait trouver l'argent nécessaire au financement de l'école.
Je frappais à toutes les portes. Et j'ai frappé, entre autres, à la porte du directeur des enseignements supérieurs au ministère de l'Éducation nationale, M. Donzelot. Et M. Donzelot était un administrateur qui n'était pas un bureaucrate. Si l'idée lui semblait bonne, il a dit « on y va ». Et il m'a tout de suite offert, en anciens francs, 4 millions. Donc ça me suffisait pour démarrer.
Elle m'a demandé de rentrer des États-Unis pour l'aider à créer son école d'été. Donc il y a 50 ans, Cécile, jeune femme, soquette blanche et grands yeux bleus, a ouvert l'école devant 30 jeunes physiciens venant pour moitié de France et moitié de tous les pays d'Europe et d'ailleurs, pour leur raconter de sa voix douce à quel régime draconien ils allaient être soumis pendant 8 semaines.
Cécile Dewitt-Morette, donc on l'a découvert en arrivant ici, avec son mari extrêmement strict, nous faisant des cours difficiles mais profonds, et puis un couple admirable qui était le couple de teufs qui faisait marcher la machine, qui arrivait à ce que tout le monde ait une couverture, que tout le monde ait à peu près à manger, et ainsi de suite. On vivait dans la boue d'ailleurs à l'époque, dans des conditions qui étaient franchement très primitives, mais justement ça rapprochait peut-être encore plus les gens.
Ah, c'était extrêmement spartiate, le confort était très sommaire, on logeait dans des petits chalets en bois à peine aménagés. La salle de cours était dans un vieux chalet. On était assis sur des chaises en toile, le tableau était très sommaire, les discussions se faisaient à l'extérieur, sur les pelouses. Non, c'était C'était sommaire, mais en même temps très sympathique, très bonne franquette. Et donc une ambiance extrêmement agréable.
2 mois durant, 6 jours par semaine, ces apprentis physiciens qui ont accepté de faire le deuil de leurs vacances vont pouvoir mesurer l'étendue de leurs lacunes.
Le premier cours de la première session a été un cours de mécanique quantique par Léon Van Hove. Et je lui avais demandé de faire un cours tel qu'à la fin de son cours, les gens puissent eux-mêmes travailler en mécanique quantique et éventuellement faire dans leur université d'origine un cours de mécanique quantique.
L'enseignement de Bryce DeWitt, le mari de Cécile, est basé sur une autre démarche.
J'ai expliqué la mécanique quantique pas du point de vue de Schrödinger et la fonction d'onde, mais du point de vue de Heisenberg avec la mécanique des matrices, la mécanique quantique des matrices. Et j'avais pensé que c'était bien pour les Français d'apprendre quelque chose qui ne venait pas directement de Broglie.
Oh, ça a été le choc. Le rythme n'était pas le même. Donc ça a été le choc absolu. On était plongés là-dedans. On a travaillé comme des fous et on a appris en 2 mois ce qu'on aurait appris en 2 ans d'université aux États-Unis.
On était dans une situation, on était mélangés dans une ambiance plus internationale ou plus américaine, et très naturellement les questions venaient. Alors quelquefois c'était des questions qui nous passaient maintenant dessus. Hein. On était constamment dans la situation d'avoir la langue pendante, de comprendre que la moitié de ce qu'on écoutait. Mais la liberté de poser la question était une éducation en soi.
Dès les premières années, l'école compte parmi ses enseignants des stars déjà consacrées de la physique. Tout d'abord, Wolfgang Pauli, l'un des pionniers de la mécanique quantique et pacifiste convaincu durant la guerre. Einstein disait qu'il avait mieux compris la relativité que lui-même.
Monsieur Pauli. J'ai vu Monsieur Pauli en chair et en os. Alors pour l'homme qui avait introduit le principe d'exclusion, de Pauli, c'était une espèce de mythe. J'ai rencontré un mythe. Un mythe qui s'est révélé un professeur détestable parce qu'il n'effaçait jamais le tableau. Alors lui, vous devez voir ce qu'il écrivait, mais il écrivait couche sur couche, ce qui fait qu'au bout d'une demi-heure, le tableau est uniformément blanc. Par conséquent, bon, vous n'avez plus rien.
Il y avait un certain nombre de scientifiques venant des États-Unis comme enseignants de tout à fait premier plan, en particulier parmi eux Enrico Fermi, qui est la personne la plus intelligente que j'ai rencontrée dans ma vie, et qui malgré ça était quelqu'un de modeste, sans aucune arrogance.
Enrico Fermi, un autre prix Nobel, qui rend visite à l'école lors de la session de 1954, est le concepteur de la première pile nucléaire avant-guerre, puis l'un des principaux conseillers scientifiques au projet Manhattan, à l'origine de la bombe atomique.
La bombe atomique apparaissait comme une chose véritablement horrible, mais ça avait été la chose qui avait mis fin à la guerre, incontestablement. Donc, et par ailleurs, l'énergie atomique était quelque chose qu'on voyait d'une façon très positive. On n'aurait pas imaginé à cette époque-là les réactions antinucléaires qui existent maintenant.
Toute théorique qu'elle soit, l'école des Houches n'échappe pas au contexte politique international, la guerre froide.
L'école a été attaquée très violemment par l'extrême gauche dès sa formation en 1951. Elle a été considérée comme un pont américain pour influencer la science française. C'était à l'époque où il existait des concepts complètement fous de sciences bourgeoises, de sciences prolétariennes, des conneries. Quand on entend ça maintenant, on rougit d'avoir même lu ça, ces choses-là.
Juste après le Spoutnik russe, on s'est beaucoup inquiété du retard scientifique dans lequel se trouvaient les pays de l'Ouest. Et il a été décidé que l'OTAN aiderait à établir une coopération internationale en physique à destination des pays membres de l'OTAN, mais aussi à d'autres. Et pour ce faire, on a créé le comité scientifique de l'OTAN.
Cécile Dewitt saisit l'occasion de la nomination de Norman Ramsay à la tête de ce comité pour lui faire part de ses difficultés
Cécile came to my office
Cécile est venue à mon bureau des larmes dans les yeux. Une chose terrible venait d'arriver. Le gouvernement français venait de découvrir que la majorité des étudiants aux Ouches n'étaient pas français. Et le gouvernement français payait 10 ou 20 000 dollars par an pour compenser les pertes inhérentes à ce genre d'institution. Et ils allaient arrêter de payer. Et Cécile allait devoir fermer. Je ne voyais rien de pire que d'être ici pour encourager la coopération scientifique internationale, alors que ce qui, à ma connaissance, allait le plus dans ce sens était sur le point de fermer. J'ai dit que je ferais de mon mieux. Et avec l'aide de la Fondation Ford, qui m'avait déjà proposé de m'aider, même temporairement, on a pu financer l'année à venir.
Donc, par la suite, on a reçu très généreusement beaucoup d'argent de l'OTAN. Et je veux dire que les premières années, c'était extrêmement sympathique parce que les premiers directeurs de la division scientifique, Norman Ramsey, Frédéric Seitz, Bill Nirenberg, donnaient l'argent sans imposer aucune condition. La seule chose qui les intéressait, c'était la valeur scientifique du projet.
Alors que le Parti communiste dénonce la mainmise de l'impérialisme américain sur la science française, l'école des Ouches invite 2 professeurs soviétiques au cours de la session d'été de 1958.
It's easy to see because of this expression and that n of x.
Elle continuera à recevoir régulièrement étudiants et conférenciers des pays de l'Est. Qu'ils soient de part et d'autre du rideau de fer, ces physiciens seront dans les 30 années à venir de plus en plus courtisés par les pouvoirs politiques, militaires ou industriels, y compris sur des axes de recherche parfois abracadabrants.
Ils étaient à la recherche d'un physicien qui leur construirait une machine antigravitationnelle. Alors ils se sont tournés vers moi, car j'avais eu un premier prix au concours de la Fondation pour la recherche sur la gravité. À cette époque, seulement 10 ans après Hiroshima et Nagasaki, et 2 ans et demi après la bombe à hydrogène, les physiciens étaient considérés comme de vrais dieux.
En 1958, l'école a rempli son objectif, ramener la physique française au niveau international. La formation s'enrichit alors de sessions thématiques. Elle s'adresse à des étudiants déjà formés qui parviennent au seuil du statut de chercheur à un moment où la frontière entre enseignants et élèves s'estompe.
Je suis revenu ici en 1964 comme directeur scientifique. J'avais la responsabilité avec mon ami André Blandin d'organiser une session sur ce qu'on appelait alors l'optique et l'électronique quantique. Les lasers venaient juste d'être mis au point 2 ans auparavant et toute une série de problèmes nouveaux se posaient. Et nous avions invité les grands spécialistes de l'époque, Willis Lamb, Roy Glauber, Nicolas Bloembergen, Jean Brossel, qui avaient fait le point un petit peu sur la nouvelle physique qui apparaissait à l'époque. Et c'était encore une session qui durait 2 mois. La plupart des conférenciers restaient les 2 mois, assistaient au cours des uns des autres et discutaient en permanence pendant ces cours, ce qui était pour les participants à cette session une occasion exceptionnelle de rentrer dans le sujet, d'apprendre beaucoup de choses.
En physique, la hiérarchie n'existe essentiellement pas, et en tout cas pas la hiérarchie des âges. Et ici, c'était très caractéristique. Le jeune qui est là, on se sent très proche de lui parce qu'on a été dans la même situation. Et d'une certaine façon, on est encore dans la même situation lorsqu'on change de sujet et qu'on veut apprendre. Bon, par exemple, est venu ici à Bragam une certaine année. Bragam était directeur de la physique au CEA. Il est venu parce qu'il connaissait bien la résonance magnétique et étant devenu directeur de la physique, il fallait qu'il comprenne quelque chose à la physique des particules. Il est venu comme élève, en tant que directeur d'un département, il est venu comme élève suivre des cours de physique des particules.
Comme l'école a réussi à faire entrer son enseignement à l'université, une nouvelle étape commence. Les Ouches décident de traiter plus en profondeur certains thèmes de recherche et organisent 2 sessions au lieu d'une seule. Nous sommes au milieu des années 70.
À travers la différence des buts recherchés, il y a certaines constantes qu'on continue à préserver. Alors, ces constantes, c'est la longueur des cours, le caractère très pédagogique des cours, d'être large, le fait d'éviter toute spécialisation extrême qui est très néfaste et qui, malheureusement, est l'un des grands défauts de la science moderne, c'est que les gens ont tendance très tôt, beaucoup trop tôt, à vouloir avancer. Alors évidemment, il faut avancer, il faut creuser un sillon fort en avant, mais en même temps, quand on creuse un sillon très fort, on risque ensuite toute sa vie de rester englué dans ce sillon. Donc il faut, dès le départ, avoir des intérêts un petit peu larges. Et puis d'autre part, avoir des intérêts larges, ça aide aussi à creuser un sillon.
Dans la même dynamique, une nouvelle structure est créée en 1977, le Centre de physique des Ouches. Ici, il ne s'agit plus d'enseigner, mais d'offrir un lieu de débat à des chercheurs de toutes nationalités déjà confirmés.
Il y avait un besoin qui s'est développé et qui se développait dans des tas d'autres endroits, de pouvoir accueillir les physiciens pour ce qu'on appelle des ateliers, donc des séances de travail sur des sujets chauds, donc là où on fait vraiment de la recherche, et c'est moins de l'enseignement que de la recherche, de la discussion, échange d'idées, souvent polémiques, discussions, sur des sujets actifs, chauds, pointus. L'école est passée progressivement d'un régime où elle fonctionnait juste l'été et elle était en veille le reste de l'année, à l'époque actuelle où depuis une dizaine d'années, elle fonctionne en continu.
Aujourd'hui, la réussite des sessions hivernales du Centre de physique ne concerne pas seulement les chercheurs de haut niveau. Son interdisciplinarité ouvre de nouvelles pistes vers une façon différente d'enseigner, renouant avec l'idée initiale de l'école d'été.
Il y a eu cet hiver, ici aux Ouches, un séminaire Lavoisier organisé par 3 écoles qui étaient l'école normale, l'X et nous, physique et chimie, et qui réunissait des élèves des 3 écoles sur l'invention physico-chimique. Comment on fait de nouveaux médicaments, comment on fait de nouveaux aliments. Des choses comme ça qui paraissent très différentes de l'esprit initial de l'école, mais qui sont en un sens là où est véritablement l'imagination de nos jours. Et là, on a réussi à avoir un public de ces élèves des 3 écoles qui était extraordinairement résonnant. Et on va en faire un livre d'ailleurs.
Autre chose qui est très étrange avec ces condensats, c'est puisqu'on peut manipuler A, on peut le faire très grand, donc on peut rentrer dans le régime où n(a) cube n'est plus très petite-devant 1, c'est-à-dire que la théorie de Bogoliubov commence à devenir marginale, quoi.
Mais comment vous manipulez A? Parce que A, c'est le rayon de l'atome, en gros.
Ah non, c'est beaucoup plus gros.
C'est beaucoup plus gros?
Ah oui. Ben, les A qu'on a typiquement dans nature, comme ça, c'est 5 nanomètres, donc 50 angstroms. Un atome, ça fait 3 angstroms.
Ah oui, d'accord, c'est vrai.
Quand on arrive aux Ouches maintenant, 50 ans après le début, on est vraiment complètement impressionné. C'est-à-dire que tous les grands noms de la physique du XXe siècle, enfin de la deuxième moitié du XXe siècle, sont passés par là. Je pense que si on prend la liste des prix Nobel et la liste des intervenants aux Ouches, ces 2 listes vraiment ont une similarité étonnante. Donc la première chose, c'est d'être intimidé. Et puis la deuxième chose qu'on se dit, c'est qu'il faut essayer de faire aussi bien, c'est-à-dire qu'il va falloir essayer de deviner maintenant qui aura le prix Nobel dans 20 ans. Donc il faut essayer de trouver non seulement les bonnes personnes, mais également les bons thèmes. C'est-à-dire quels seront les thèmes qui, dans 20 ans, auront pris une ampleur telle qui seront nobelisables, entre guillemets, alors que pour le moment, c'est juste des petits domaines en train d'émerger.
Donc, à suivre.
Par le président de l'Université Grenoble-Alpes, Patrick Lévy, à notre lauréate, juste avant, je vais dire quelques mots sur ce prix international Cécile Dewitt, École de physique des Ouches, qui a été créé cette année, c'est en 2019, grâce au soutien de toutes nos tutelles. Donc c'est un prix international annuel pour des personnes de moins de 55 ans qui sont passées aux Ouches, soit comme élèves, soit comme enseignants, soit même comme organisateurs. Et donc ça sera un prix annuel. Il est pas mal doté, c'est à peu près 15 000 €. Et nous avons maintenant envoyé des tas d'annonces. Disons, le prix a été donc lancé cette année, mais il va continuer dans les années qui viennent. Et donc, il est international, ouvert à toute nationalité, en fait. Et nous espérons bien voir et nous avons déjà eu des candidatures de très haut niveau. Et c'est donc pour encourager des chercheurs qui ne sont pas à la fin de leur carrière, mais sont en cours de carrière, pour développer la suite de leur recherche et leur donner une meilleure visibilité. Donc, comme une bonne nouvelle n'arrive jamais toute seule, pour Francesca Ferlaino, notre lauréate, qui est professeure à l'Université d'Innsbruck, elle a reçu dans une séance solennelle à l'Académie des sciences mardi dernier sa médaille, et on lui a demandé de venir nous faire un petit exposé sur ses travaux de recherche. Et donc avant cela, je passe la parole à Patrick, qui va nous dire quelques mots sur la lauréate.
Merci beaucoup. Alors j'aurais pu essayer de parler en anglais, mais déjà comme ça en français, la description de l'éloge de Francesca n'est pas si simple, donc je vais rester en français en fait. Pour dire d'abord qu'on est très heureux de ce prix. Et évidemment, l'occasion est formidable parce que Kip a expliqué avec un brio incroyable cette aventure, parce qu'aussi on a parlé et très bien de Cécile Dewitt-Morette, et donc effectivement l'événement est tout particulier. Alors, ce que je dois dire de Francesca Ferlaino, c'est qu'elle est professeure de physique à l'université avec laquelle on est d'ailleurs très liés, qui est l'Université d'Innsbruck, et directrice de recherche dans un centre qui s'appelle ICOKI, qui est l'Institute for Quantum Optics and Quantum Information de l'Académie des sciences autrichiennes. Alors je vais résumer très rapidement, et vous me pardonnerez parce que je ne maîtrise évidemment pas les concepts qui sont là, mais je vais essayer de l'expliquer le plus clairement possible. Donc Francesca a effectué des travaux très remarquables sur les gaz d'atomes ultra-froids, ce qu'elle va probablement expliquer. Elle a bénéficié aussi de quelque chose qui est très important pour des chercheurs et qui démontre leur capacité à avoir une équipe de recherche autonome, notamment un Start Prize de la FWF et un Starting Rank de l'ERC en 2009. Et elle a donc obtenu de résultats très importants sur la physique à petit nombre de corps et des états d'Efimov. Elle a ensuite étudié les propriétés quantiques collectives de l'atome d'herbium, qui est un atome qui possède un grand moment magnétique. Et donc l'interaction dipôle-dipôle magnétique est à longue portée anisotrope. Et donc associée à l'interaction de contact qui est à courte portée isotrope, cette interaction vient considérablement enrichir la panoplie des phases quantiques à très basse température. Donc ces découvertes dont elle va nous parler sur les propriétés des gaz dipolaires, aussi bien bosoniques que fermioniques, sont particulièrement spectaculaires. Et on peut citer en particulier l'observation de résonances de collision, dites de Fano-Fershbach, avec un espacement en énergie entre ces résonances très bien décrites par une théorie de matrice aléatoire, une signature de chaos dans le domaine quantique, et aussi l'étude du modèle de Bose-Hubbard avec interaction de contact et dipolaire et l'observation d'un mode de roton précurseur d'un nouvel état de la matière, un état superfluide, dit supersolide. Je suis à peu près arrivé. Voilà. Donc ceci étant dit, on va l'écouter, mais on peut dire que ces travaux ouvrent la voie à une meilleure compréhension de la physique quantique à n-corps et à de futures applications très importantes en simulation et en ingénierie quantique. Donc, comme Christophe l'a dit, l'Académie lui a rendu à l'Institut de France un hommage à l'occasion de la remise solennelle de son prix sous la coupole, donc le 15 octobre, il y a 2 jours. Mais on est extrêmement heureux de pouvoir aujourd'hui célébrer ce prix et le lui remettre. Merci beaucoup. En fait, je suis juste, donc le prix a déjà été remis, évidemment, mais on va remettre, alors on va d'abord mettre le micro à Francesca, ce qui semble important. Kip fait ça très bien, fait ça très bien. Voilà. Et on va lui remettre 2 choses qui vont être encombrantes pour parler, mais on va lui remettre la médaille d'or de l'Université de Grenoble. Voilà.
Merci.
Et des fleurs qui vont avec, mais vous avez le droit de ne pas les porter tout de suite. On peut Et je vous laisse la parole.
Merci beaucoup. C'est évidemment pour moi un énorme plaisir d'être ici ce soir. Merci d'avoir resté pour cette deuxième partie. Merci pour le prix. Merci pour me donner l'opportunité incroyable de commencer une traduction avec ce prix pour Dewitt-Morette. Et merci à Chris, la fille qui est là. Merci de nous donner une chaleur très grande qui nous fait aussi comprendre quelle est l'importance des gens qui sont ensemble pour chercher de comprendre la physique, que ce n'est pas nécessairement quelque chose qui va apporter de l'argent ou qui va apporter une gratification immédiate, mais c'est vraiment le travail des années, la construction d'une communauté, l'enthousiasme, la curiosité, la pensée au dehors des limites normales. Et tout ça, moi je suis très émue, je dois dire, moi je suis italienne, donc pardon en français, mais je suis extrêmement émue. Je suis émue de voir tellement de jeunes personnes aujourd'hui. J'étais émue de voir les photos et de voir tellement de participation. Les Ouches, même pour moi, que je ne suis pas française, que je suis arrivée à Les Ouches la première fois comme étudiante, a eu vraiment un impact très important sur beaucoup de gens, partout dans le monde. Et vraiment, des amitiés scientifiques se sont créées à Les Ouches. On a eu des nouvelles idées et je pense que chaque personne que je connais peut vous dire une petite histoire de Les Ouches, de qu'est-ce qu'il a ouvert. Et une chose qui m'a toujours très frappée, là je n'ai pas préparé ce discours, donc pardon, c'est que quand quelqu'un devient aujourd'hui directeur de quelque chose, la première chose qu'on pense comme professeur, on doit faire de l'enseignement, on doit faire de la recherche, on a plein de gens qui nous demandent des choses. Donc quand on doit faire le directeur de quelque chose, bon, c'est important, mais ça vient aussi avec un peu de un autre travail à faire. Tandis les directeurs de Les Ouches, ils ont une fierté d'un rôle qui est très important et qu'ils connaissent. Et bon, on a Christophe Salomon aujourd'hui qui est le directeur de Les Ouches maintenant, et on voit l'esprit de fieresse de représenter quelque chose qui est important, qui a été important, qui a un significat extrêmement grand dans la société scientifique partout. Et donc, vous pouvez bien comprendre quelle est l'émotion pour moi d'être la première lauréate de ce prix. Et bon, et maintenant, je vais vous dire pourquoi j'ai eu ce prix. Donc, restez avec moi encore quelques minutes. Donnez-moi un instant pour préparer l'ordinateur. Mais encore merci vraiment de tout. Thank you. I think they gave it to me. Bon, je vais mettre un instant. Ah, il veut quelque chose de moi. Un instant seulement, pardon. J'ai mis un nouveau. Non, il n'aime pas le pointer. Christophe, tu avais le point, tu avais l'autre ici? Non. C'est où? Merci. That doesn't work for me. I'm sorry. Ouais, je sais pas. Bon, on va voir. So I will now switch to English. And so let me say that the only point of view that I can give on the School of Les Ouches is the one of a participant, but also a little complementary point of view with respect to what we heard today, because I never met Cécile Dewitt-Morette, but very importantly, I met the person she knew. So I could see her reflected in the eyes of the person, telling story about her. And I have to say that the image that came out is an extremely inspiring image. And especially for a woman and for the important role of women in science she's now having as a role model. So. And to go on, I would like to tell you my experience with Les Houches. So my experience with Les Houches started in '99. So I was a student in the University of Naples in South Italy. And so there was a little poster outside of my university telling about the fantastic school in matter wave in '99. So I kind of, I was not doing any master thesis. I knew almost anything. And I was really a fresh student, so I wrote to the organizer and I asked if I can join. I was ready to pay everything by myself, and the organizer answered me, "No, you cannot. You are too young. You should wait a little bit." So my starting with Les Houches was not maybe the best, and I had to wait indeed a couple of years, and then finally in 2003 I was able to go to Les Houches, and so I also give you some picture. I mean, this was a really funny from ping pong to dancing. There was quite some dancing in that conference, and many friendship and many discussion. Here you can see the present director of Les Houches together with other colleagues. And for me, this was also very important in 2003. As I said, everybody can tell you a story about Les Houches. My story is the following. So first of all, so I met this guy, Rudy Grimm, here in the back. And actually, Les Houches was really the place where I went to him and I say, "Look, I'm finished the PhD. Can I come to Innsbruck, join your group for a little while?" And they said, "Yes, sure, just come." This was the right contact point. I mean, there was the kind of environment to really discuss things. And this was 2003. And remember 2003, this will be important later. And I also made a friendship with Luis Santos, which was a theorist in Hanover. And actually, I knew already him, but in this conference, he was super busy. He was actually almost never with us, and I was asking Luis, what's this going on? Why you go so early in your room? Why you don't participate to the discussion? He said, I'm writing a very important paper. He's a theorist, and he was writing a paper about a new type of excitation that you can have on very, very cold atom, which is called the roton. And he explained it to me in 2003, what was this achievement. And this is what I would like to explain to you today, because 15 years later, actually turned out in our experiment, we had the chance to observe what actually he was writing up during Les Houches night. And with this, I would like to start with the scientific part. And so I would like to tell you that we move now really, as Christophe already said, to very, very low temperature. And in this extremely low temperature, many interesting physics can appear. And very recently, we observed in my lab and in other two labs, one in Italy and one in Germany, a new type of state of matter, is a quantum state, which is completely paradoxical. So it's hard even to think about, because it's at the same time a fluid, a superfluid, where particle can flow without friction, and a crystal. So you have localization, solidity, crystal properties combined with superfluidity. And this is why we have been inspired by one Greek god of the ancient mythology, which is called Janus, which has a double nature. Okay, of course, Janus has a double nature of the past and the future, and our new state is a super solid and is a double nature of a crystal and a fluid. And you cannot cut these two properties. One without the other could not exist. And so we are moving to the general concept of something which is called quantum fluid. I mean, you have to imagine now to go into the quantum regime, maybe to very, very low temperature. Thermally, temperature play absolutely no role. And then you have many particles, and these particles start to interact with each other. So you can create in this way a system which is, we call, strongly correlated, many bodies with strong interaction. And this type of quantum fluid can be very diverse. And so here is just, the example of big, let's say, field of quantum fluid. On the one hand, you have the helium superfluid that you know very well. This is a liquid. And then you can move to superconductor, which are solid, or you can move to the gas phase of Bose-Einstein condensate and quantum gas, and very recently also quantum, let's say, quantum fluid of light. So you can have liquid, solid, gas, light. But this system, when you go in the quantum regime, when you allow in some way or the other interaction, they can show really very similar properties, but also very big difference. So the system which I would like to tell you about is these quantum gases. You have really to, for 1 second, imagine a normal gas. So it's made of atoms, and these atoms are extremely cold. And over the last, let's say, 2 decades, we learned how to make it so cold such that all the atoms behave in the same way and enter in a new state, which is called Bose-Einstein condensate. So you have 1 million of atoms behaving as a macroatom, but this is not a molecule. It's a gas of particle, but meanwhile, the interaction is so strong that you cannot extract one atom without affecting all your system. And so over the years, we, let's say, understood how to reach extremely cold temperature. We, in the sense of our community, of course, and you saw in the previous film many key players for all this development. And so we also learned how to trap this gas. Actually, we made a cage, like in a little prison made of light. And so we can trap a gas with light. And then we discover how to, let's say, use the interaction and which type of interaction, how do these atoms speak to each other. And we also, let's say, try to train them to speak in the way we want. That means to interact in the way we want. We then, of course, can use the internal degree of freedom. We can use a very different geometry because we are trapping with light. We can make a crystal of light in which in every side of the crystal there is a little atom, and many more than this. And so now if we think about how do we produce this system, Manfred Mark from our group, he made a very nice video. So this is, you are looking inside our machine. Okay, we are experimentalists. This is a tube and this is a flow of atom, let's say, moving. And these are already pretty slow, and this is just an atomic beam, very slow, because we already use light to slow down the motion. Then this atomic beam is arriving in one specific point, which is called magneto-optical trap. And you saw in the Lesouche video the person that really put together the concept of the magneto-optical trap. That was then one of the directors, Jean Dalipard. And then here, all the atoms are collected. Not all the atoms, part of the atom are collected. By what? By this yellow light that you see. It's just light. And this light is trapping the atom and also cooling down. And so here we are in a regime where the atoms have microkelvin, so 10 to the -6 Kelvin. So it's already very cold, but for us it's too hot, it's way too hot. So we need something else. We switch on this resonant light, we call it, and we put with another type of laser light, we put here all together. And then here we can remove the hottest atom and then eventually enter in the Bose-Einstein condensation. This is the way we produce our quantum gas, and we let's say, go toward degeneracy. And then now the second thing I want you to know is about the interaction. Because I told you, okay, it's, you have to enter the quantum regime. Now in our experiment, the community knows how to do this, but then you need also to understand how the atoms speak to each other, interact to each other. And so, and here the interaction between the atoms can be very strong or can be very weak. But in both cases, you will have a quantum fluid. And indeed, I mean, the very nature of the quantum fluid rely on the interaction. And now, if the interaction between this particle is strong, then it's the situation in which you have superfluid helium. And if the interaction is weak, this is where you have quantum gases. Now, these are two extremes of, let's say, the scale of interaction in some sense, but still these two quantum fluids, very different, one is liquid, one is gas, they would show some very similar phenomena. For example, the phenomena of quantized vortices. So the little white hole that you see here, it's a little vortices in a superfluid helium. And the vortices are quantized, so they cannot become very big vortices, let's say hole of matter. What they do, they split into 2, 3, 4, depending on how fast, let's say, a glass with superfluid helium is rotated. And the same type of physics you can see in gases. So this is now really a gas. And people, especially in France, were really able to push this technology to understand how to relate, how to add angular momentum in this system. So very different system with some very similar properties. But in reality, there is another type of properties which are really very different between superfluid helium and quantum gases. And this is the concept is related to the concept of quasi-particle. Basically, if you have any system and you shake the system, you are exciting sort of the system. Doesn't matter which one it is. But now, if you are in the quantum regime, this excitation depends very much on the internal interaction of the atom itself. And so quasi-particle is the word, let's say, created to define excitation, which are dressed, like you put a nice dress, by the interaction between the atom. And so this was a key concept really to explain superfluid helium. And also a key concept and at the center of a very strong debate to try to understand what is the behavior of this special fluid. Indeed, this, the idea of quasi-particle opened a very intense scientific discussion back in the 36, 38. And so there was Kapitsa. It's a very beautiful story from the historical point of view, because, I don't know if beautiful, but very interesting. So Kapitsa, he was working in Cambridge in the UK. And so in April 34, he finished a machine which was able to liquefy helium. Let's say this is more or less the month where he got the first drop of helium superfluid. And then in September, at least what I was reading, there are different versions, he went to the US, to the Soviet Union to celebrate the 100 years of Mendeley table. So, and then he was never allowed to go back to UK. So he had to stay, so let's say several agencies and armies sort of, they blocked him in the Soviet Union and he could not go back. So he got the first drop of helium liquid, but now from September on, his main life had to stay in the Soviet Union. But he was also a very strong man, and he said, okay, you want me to stay here? I stay here, but you give me enough money to build a new liquefier. And this is what he did. And then he did a lot of study, and he actually looked this super leak of helium superfluid, and he called it this strange liquid, he called it the superfluid in analogy with superconductor. Okay, look at the year. This is 37, okay, just a few years before the official start of the Second World War. And simultaneously, there was Fritz London. I mean, France really played a very important role in this period to become a home for many scientists escaping from their country. Indeed, Fritz London escaped from Berlin and he reached Paris in 36, let's say, and he started to understand and to study more the superfluid, what were the strange behavior. And then in 1938, there was another very important theorist, Tizza, that escaped from Hungary and again went in Paris at the Institut l'Institut Poincaré. And so these two met together, actually, and they started to theoretically work to understand the reason of the special properties of a superfluid, which basically, if you take a helium superfluid in a glass, any little hole that you would even not see are big enough to make the liquid to percolate. Those are the idea of super leak. And then there was Landau in 1936. Actually, he was in prison in the Soviet Union, and he can go out of the prison thanks to, let's say, the diplomatic work of Kapitsa, and it was studying and proposing a different interpretation of superfluidity, which was based on this concept which I told you of quasi-particle. And so he postulated was really, I mean, it was not really a rigorous theoretical demonstration. He simply had an idea that maybe there are these quasi-particles that exist, and he also identified two different types of quasi-particles, phonon and rotons. And so the roton itself, this is the the energy of the quasi-particle, and so the roton itself is a special excitation which appear at very large momentum. I will tell you more later. And now London, first of all, Landau, he never commented on the theory of London officially. He had a completely different point of view, and he thought that superfluidity should be connected with the Bose-Einstein condensation, so all the particles occupy a single quantum state. But Landau never commented on this theory, while London commented in the theory of Landau, and this is what he's writing. So, I mean, Landau is searching an explanation based on the shaky grounds of imaginary roton. There is unfortunately no indication that there is anything like a roton, at least one search in vain for a definition of this word. Okay, so it's clearly they were in very big, let's say, conflict, and actually they died unfortunately too early to realize that both of them were actually right. And then several years later, so almost 65 years later, experimentalists could confirm, so this is the curve of Landau, so it's a linear part of excitation, which is the phonon, and then this minimum, which is the roton. And this point here, you see, is the experimental confirmation that indeed this roton type of excitation exists. Now, I want to give you a little sense of what this excitation means, because these are only names. So, the phonon excitation, you have to think like you have a quantum fluid, you shake the quantum fluid, and the quantum fluid moves as a jelly. Okay, so it's a jelly moving, and the collective excitation has one specific frequency. Whereas the roton one, you have to imagine as a little density modulation that appear on the quantum fluid. And now, this density modulation by Nozière, it was put in context to the idea that maybe when the system is close to this roton excitation, where this density modulation can appear, maybe this is the right way to think that the system wants to become a crystal. So he's not able to become a crystal, but he would like to become a crystal because he starts to make, let's say, pattern, a regular pattern with some localization, like a crystal. And then starting with this idea and some further other idea, it came an idea of a novel type of state of matter, which is called supersolid. And this so first of all, quantum physicists, I'm learning they love the word super because we have superconductor, superfluid, and now supersolid, but it's really because the properties are exceptional. So this state is a state which has the rigidity of a solid, let's say, but still the particles are flowing like a superfluid wave. This was a theoretical oddity. It was extremely strange to imagine something like this, and was, I mean, at the beginning, let's say, discussed as a kind of a paradox of quantum physics in some sense, that I mean this type of state within the rules of quantum mechanics could exist. But actually the search really started very intensively in superfluid to try to find regime of interaction where actually this could happen. And the observation one observation came in 2004 in helium, superfluid, by Kim and Chan. Look at the title, published in Nature, Probable Observation of a Supersolid Helium Phase. And then when this happened, of course, there was a lot of media press having the attention because a really generic, new, very counterintuitive state of matter would be invented. And at a very big visibility, this result. But now, if you go into the detail of this title, you can kind of highlight few words. Maybe a possible new form of matter, glimpse, probable discover. There was some shakiness, and actually there was an intense debate by the scientific community to try to understand if the observation by Kim and Chang were actually really confirming the existence of a supersolid or not. And after 8 years, there was the same two authors published in PRL in 2012, another paper actually saying that the original observation have now a different explanation that cannot be directly connected with the existence of a supersolid state. And then again, there was some press release, supersolidity loses its luster. But this, I think, that was a very nice example of how, I mean, quantum physics or physicists in general are challenged because you observe something and it doesn't come with a subtitle. So you have to undecode all the behavior and try to find an explanation. Sometimes there are explanations that you are not imagining, and so this is why it's part of being scientists also to expose ourselves to interpretation that might be not fully correct. And this was, let's say, the end of the story for the superfluid. But now, if you look back at the paper of Nozière, in his paper speaking about the roton, there is a sentence that says, if the interaction in this quantum fluid is weak, so our quantum gas, as I define it, then you will not have a roton excitation. And this indeed, when the community started to study, let's say, collective excitation, this is really the case. I mean, this is the energy spectrum of the excitation, and you see that there is no roton minimum. But then, is this now game over, the end of the story? And now come the year 2003. And the scientist which I showed you before, the theorist, Luis Santos, because actually he and also other group at the same time gave an answer to this question. No, it's not game over. Just you need a very special type or flavor of your interaction. And so the type of interaction that you need is magnetic one. So far, everything was considered to be interaction in which two atoms, they feel each other just if they touch. But actually, if you think about magnetic interaction, so like magnet, the one you use in your fridge, then you see that the interaction can be already long range. Even if it's weak, you can add a correlation which is long range. And so there are, and what Luis Santos, Jorash Lapnikov, and Maciek Levenstein said in 2003, or proposed, is to have a quantum gases of particles that interact both with the contact, so short-range interaction, and the long-range magnetic type of interaction. And actually also they proposed that these two types of interaction can be, let's say, controlled separately. And this was really opening a lot of questions on how highly magnetic dipolar particles would interact and what will change in the physics if we consider this interaction. And this was then the prediction that they had. Now, one problem is that the atom that in our community we were used to, they don't have a dipole moment. They don't interact via dipole-dipole interaction because you need that this atom to be highly magnetic. And so we kind of was not enough the magnetic moment of the known atom in quantum physics. On the other hand, one can think to more complex system, but then it's very hard to put it really in the quantum regime. And then, I mean, there was a new exciting opportunity coming up, and is, let's say, to produce quantum gases of a new class of atom, which are highly magnetic. And this is the periodic table, and this is the achievement of Bose-Einstein condensate over the year. And now you can see how the things produced, here is where there was the prediction and no real magnetic atom available. And then very recently, there have been these two species in the red, erbium and dysprosium, to be produced in quantum regime, so both condensed, and those are really the promised candidate. Chromium is also magnetic, but not enough to see the physics. So I don't want to go very long on the history, but there have been a lot of study to produce different platforms, so both with the degenerate Fermi gas and bosonic gas. We produced in 2012, so pretty recently, the first Bose-Einstein condensate of erbium. Then we also produced with the Fermi gas the molecule, and very recently we are also combining this erbium and dysprosium to create a mixture. And also work with the other strongly atomic species, dysprosium, have been done in the group of Benjamin Leff in Stanford. So these were very promising atoms, and so the question was, okay, now we have a quantum gas, a quantum system with long-range interaction. Can we see a roton? And so now, thanks really to the commitment of our team, and in particularly one member, which is Daniel Petter, he kind of developed a way to measure the spectrum of excitation. So remember, the spectrum can be linear, like in the without dipolar interaction or with weak dipolar interaction. And then if you now decrease the contact interaction, so the system will change and eventually rotonize. And so this is what we observed. Now we learn how to control the interaction, and we are now measuring the spectrum using a technique known as Bragg spectroscopy, and then you see how the spectrum of excitation change and indeed develop this type of minimum. So this was really, after 15 years from the theoretical prediction, the first observation of this roton excitation in our system. And this was just the first point, because if now the spectrum of the excitation softened completely and touched zero, then what does it mean? Is that it costs no energy to create an excitation. It means that everything any very infinitesimal event can make the system to develop this density modulation. And then the density modulation in-trap, now imagine, is a gas that spontaneously starts to be modulated in density. But it's just a quantum gas. There is no external potential imprinting any shape. They are just, due to the interaction, try to align and make this density wave. And now this is the density wave in a real space, so in the real density, and then in momentum space you would see this modulation as the appearance of two peaks in momentum space. It's easy in the experiment to measure momentum space, and this is what we have done. In this case, the system has just one momentum class, but then if you go completely soft, you see the spontaneous appearance of additional momentum, and with a very clear interferometric signal. And so, and this is directly connected with the appearance, the spontaneous appearance of density modulation. And you can even go further and to have even a more prominent pattern. And then the question is, now the density modulation, this localization, the breaking of the continuous symmetry spontaneously appear. Can it be that the ground state of the system is a supersolid? So we were really not, let's say, imagining to go so far in this research when we studied first the roton, which actually was really a study done conceptually, very importantly, by our postdoc Lauriane Chaumont. And this was the next question, and I don't want, it's already late, I don't want to go into detail, but actually in a later experiment we could really demonstrate that yes, indeed, this gas made of many little magnets and many little atoms would spontaneously create a density modulation is a finite set like a crystal. And simultaneously, there is the global phase coherence. So we studied many different properties of phase coherence. You know, here the system have really all the atoms a global phase and the density pattern of a crystalline phase. And very recently, we also studied the excitation spectrum. So this was for us really the first study and confirmation of a supersolid state. As I mentioned before, there are two other groups, one in Pisa experimental group and one in Stuttgart, that they also conducted beautiful experiment in this topic and having a very similar result than ours. And so now this is the starting point for us to learn more about this novel, strange state of quantum matter and to understand the property. In particularly, we want to study how the vortices, how the superfluid flow, how the frictionless movement of the particle really are entering into this state. So all this was to give you just a little bit of the sense of what we are doing in the team, and also to explain you a little bit for what I got the prize. But I also have to tell you that in general, every prize and recognition is not only one-man result. Is really the result of a team. And if you're an experimentalist, the team is even more crucial. So, and I would like now to introduce you the two teams that have worked in this latest result, which I show, that is the super solid. And so the rare team with Philip, Arno, Max, Manfred, Gianmaria, Sandra, and Claudia. And here really, Manfred took a very important role, and the Erbium team, this is a very old picture. The people working on the supersolid is Lauriane Chamau with a very important role, Manfred, Daniel Petter, and Gabriele Natale. And so all the team is here in Grenoble. We are all here. We came yesterday night with two big cars. And so if you have time, I think they will be happy to discuss with you. They're in the second row, and this is our team. And if you want to learn more, please visit our website. And then let me also say something more personal. It is not always very easy to do science. There are a lot of sacrifice that one has to do, a lot of commitment. And of course, there is another important part of the life, which is the family, and to try to get the right balance between the family and between this so intense work that we are doing as a scientist. And it's not always easy. And I have to say that from the women point of view, is actually many times a challenge, a very nice challenge, but a challenge. And nothing, absolutely nothing of what I show you today and nothing of what I have achieved so far could have ever be happening without, let's say, really my family. They are also here tonight, so my partner, Peyo, that it's really supporting me, and my two kids, Michele and Coralur, and this is really important because they actually really participate into the big picture of being a scientist and human at the same time. So with this, I would like to thank you very much, and thank you for this fantastic prize, and yeah.
Thank you very much. Thank you very much, Francesca, for these very beautiful images and to convey the message that you have done during your scientific career, you know, so successfully. We have time for a couple of questions, and then we will conclude with a little word of Chris Dewitt, the daughter of Cécile. But before that, we do a couple of questions. If someone has a question on the cold atom physics or the life of a woman who is both a mother and a great physicist.
People are a bit tired. There is one hand over there. I see. One.
Okay, microphone up there.
Allô, bonjour. Oui, bonjour. Merci pour vos explications. Et en fait, je suis en 3e année de licence de physique. Et avec les informations et les cours que j'ai actuellement, on n'a aucun moyen de comprendre comment on peut refroidir quelque chose avec de la lumière, en fait. Et si vous pouviez peut-être synthétiser comment vous faites, ça pourrait...
Oui, vous avez raison, je ne pouvais pas vraiment refaire toute la physique des atomes froids, autrement je ne serais jamais arrivée au supersolide. Bon, c'est pas facile. Les atomes, ils ont chaque atome a une structure interne de niveau énergétique. Et ces niveaux sont quantisés. Ça veut dire qu'il y a vraiment, c'est comme une échelle. Il a un niveau et puis le suivant. Non, maintenant, si vous mettez un laser qui a exactement l'énergie de ces deux niveaux, l'atome, qu'est-ce qu'il fait? Il va absorber et va être dans un niveau excité. Rien ne reste dans le niveau excité pour toujours, donc l'atome, il va revenir en bas. Et puis il va peut-être encore une fois absorber et redescendre. Maintenant, tout ça, comme vous voyez, je mets de l'énergie, j'enlève de l'énergie, je mets de l'énergie, j'enlève de l'énergie. Donc, il n'y a pas vraiment du refroidissement, parce que refroidissement, ça veut dire on enlève de l'énergie thermique. Mais il y a eu des scientifiques exceptionnels qui ont compris qu'en effet, il y avait un moyen d'utiliser ça et de perdre de l'énergie. Parce que maintenant, si tu as un atome et un laser qui arrive de cette direction, le laser bouge, l'atome bouge de cette direction, le laser bouge de cette direction, d'accord? L'atome va absorber l'énergie. Mais après, quand il va la perdre, il peut faire une émission à n'importe quel angle. Et maintenant, s'il le fait beaucoup de fois, une fois c'est par ici, une fois c'est par là. Et donc, les choses en moyenne deviennent zéro. Et donc, d'une certaine façon, il se refroidit parce qu'il a une émission que la moyenne devient zéro. C'est un peu difficile à expliquer, mais peut-être Christophe, il a une façon beaucoup plus simple d'expliquer, parce qu'il est vraiment un des experts mondiaux.
C'est ce qu'on appelle la pression de radiation. Hein. Ce que Francesca vient de décrire, c'est un faisceau laser exerce une pression physique. Hein, et c'est comme la queue des comètes, hein, quand une comète traverse l'univers, la queue de la comète est toujours opposée à la direction du Soleil parce que le Soleil éclaire la comète. Et donc ça exerce une force sur les atomes. Et l'idée supplémentaire que tu n'as pas juste mentionnée, c'est juste qu'il y a un recul. Quand l'atome absorbe le photon, il recule, hein, comme une balle de fusil quand on tire un coup de fusil. Eh bien, quand il absorbe le photon, il recule. Et à l'émission, ce recul fait zéro, alors qu'à l'absorption, c'est toujours dans la même direction. Et le deuxième ingrédient, c'est l'effet Doppler. Le fait que quand on bouge et qu'on va vers le faisceau laser dans l'autre sens, comme ça, la fréquence du laser est augmentée, alors que quand on va dans le même sens que le faisceau laser, la fréquence est diminuée. Et grâce à ça, on peut faire un déséquilibre pour refroidir. On peut faire un déséquilibre entre les deux pressions de radiation et conduire une force linéaire en vitesse, F égale moins alpha V. Voilà. Et ça refroidit le gaz. Évidemment, ça ne refroidit pas jusqu'à zéro, parce qu'il y a des fluctuations quantiques, et c'est Einstein qui a montré tout ça, qui a sorti une magnifique formule qui relie la température au coefficient de diffusion divisé par le coefficient de friction. Voilà. Bon. Une autre question? Oui, là-bas.
Est-ce que la compréhension d'états quantiques avec plusieurs particules et donc de plus gros volumes, ça peut avoir des applications pour comprendre les phénomènes de décohérence des systèmes quantiques, ou ça n'a pas tellement de lien?
Non, c'est extrêmement lié. La cohérence et les états fondamentaux de la matière quantique sont extrêmement liés, parce que la cohérence, ça veut dire qu'il y a une phase globale qui peut décrire un ensemble avec peut-être 1 million d'atomes, mais ils sont cohérents. C'est pour ça qu'il y a eu pas mal d'expériences. Tu sais, les lasers sont aussi un objet où il y a la lumière qui est cohérente, et tu peux prendre deux rayons de laser, non, de faisceaux, comment on dit, de beam, comment on dit beam?
Un faisceau.
Un faisceau, 2 faisceaux laser, tu peux les mettre, tu as cette interférence qui te dit, tu t'informes sur la cohérence des lasers. Bien, dans notre domaine, il y a des expériences où tu peux prendre deux condensats de Bose-Einstein et lui faire interférence comme vraiment une onde de matière. Une autre façon dans laquelle on décrit aussi notre expérience, c'est en parlant de onde de matière, qui a beaucoup de propriétés similaires de l'optique non linéaire et beaucoup de propriétés de cohérence. Donc c'est vraiment une très bonne question et très reliée.
Une autre question?
Bonsoir. First of all, thank you for this marvelous presentation. Congratulations for your award. I cannot imagine how big it is for you, someone that clearly is so passionate for what you do. And thank you so much for your presentation. My question is made by someone who is not physicist. I am like, I don't know what, but my question is if you already thought about, it's possible our reality, our existence is immersed in some kind of superfluid. I will say why I'm asking that. The alien superfluid, they have some similarities with black holes. I cannot explain what, but the two-dimensionally is, you have some similarities between the alien superfluid, with the black holes. Our universe, the beginning of our universe, before there was light during the Dark Age, it was discovered 2 years ago or last year, that is four times colder than we thought. I don't know if it's enough to make a superfluid state. And the other thing, I think it's maybe always in the physicist, is the ether, but the ether was not ether, I don't know how to say it.
L'éther.
Yes, l'éther, it was like an idea more than 100 years ago. It was never observed. But sometimes we cannot observe something, and after we can observe like the super solid. So this is my question. Thank you.
So I would say that I'm not deep enough in, let's say, black hole physics and so to say really something and to answer your question. What maybe as a general answer, I would say that we do not know, so we know that quantum mechanics and some, let's say, quantum fluid, that they usually appear at extreme condition. So it can be extreme condition of interaction, and it's not necessarily needed to be at very low temperature. It's always, I mean, a compromise between the temperature and the strength of the interaction in some sense, for some case. So I think that the border of application is something which is a very exciting topic. And maybe you want to add something? No? Yes, come here. Yeah, it was.
I will just add that I have no depth in superfluids and so you've asked a question that's somehow connected to what we both do, but connected in ways that I think neither of us really understands. And well, that's one of the glories of working in science. There are always these big unknowns, and particularly at interfaces between fields where you're just beginning to understand that there might be some connection.
Yeah.
So I think now it's time to conclude this event. I'm very happy, that you came so numerous and to listen to both extremes of very high energy and very low energy physics in the single afternoon. And to conclude, I would like to give the microphone to Chris, the daughter of Cécile, will tell us in a 1 minute, her feelings tonight, and then we will stop this ceremony.
I just want to thank everybody associated with Les Ouches and Grenoble and l'Académie des Sciences and all the other organizations for creating the prize. And then I want to conclude by an enormous thank you to Kip Thorne and to Francesca for coming and honoring my mother in this way. She would have been so thrilled to have Kip here and to have someone like Francesca chosen to be the first recipient. And I have a little gift that's from, it's books from my parents to Francesca, and Kip has inscribed one of the books, so it's...
Thank you.
Voilà, merci beaucoup. Thanks for coming, Chris. Thanks. OK, merci à tous d'être venus et bonne soirée. OK, great talk.